I'm attempting to learn calculus, which is like one of the hardest math, and I'm sick right now, and I've got a massive headache. I look like Lloyd because my barber did me dirty. This calculus usually takes like 3 to 4 months to learn. I'm watching a 12-hour tutorial, putting it on times two speed, and trying to learn it in 4 hours. So just do the math. Alright, bro, let's just lock in, bro. Please say there's like clean audio or something. Bro, please say there's like yeah, that'll do. Right, we're learning calculus. I'm in high school, math book. My writing's pretty niche. Oh, funny. Can you guys hear that? You guys hear that? You guys hear
This video is about working with rational expressions. A rational expression is a fraction, usually with variables in it. Something like x plus 2 over x squared minus 3 is a rational expression. In this video, we'll practice adding, subtracting, multiplying, and dividing rational
yeah, Chuck gets some
expressions
times two speed,
and
bro. I'm already
simplifying
bored.
them to lowest terms. We'll start with simplifying to lowest terms. Recall that if you have a fraction with just numbers in it, something like 21 over 45, we can reduce it to lowest terms by factoring the numerator
Yeah, shit, it's gonna be
and
easy,
factoring the
chat.
denominator.
Oh hell no! I didn't pay. I'm not advertising ads.
Not ready for it.
I got my lunchbox here.
And then canceling common factors. So in this example, the 3's cancel, and our fraction reduces to 7 over 15. If we want to reduce
No, I
rational
should have brought my
expressions variables into lowest
calculator
terms,
out,
we proceed the same way. First, we'll factor the numerator.
It's easy light work, bro.
And then factor the denominator. In this case, it factors to x plus 2 times x plus 2. We could also write that as x plus 2 squared. And that's the reciprocal of the fraction on the denominator. So here we
4 and 5, like 4 and 5 or like 2 and 5. It's like, yeah, times that.
4/5 times 3 halves, and that gives us the numerator. And x squared minus 16, that's a difference of 2. So we can't and 15, 2 are not 2 minus
Go to the hard
by
stuff.
rational expressions by multiplying and writing them in terms of the.
No, bro, this is light work. What's now? I think we've gone too far. That was F. Oh yeah, we got too far. Oh yeah, we started.
Write each of my two rational expressions by multiplying 2 as 2 times x plus 1. I'll write it in factor
Guys
form.
got
And I
audio?
notice that compared to least common denominator, I'm missing the factor of x minus 1. So I multiply the numerator and the denominator by x minus 1. I just need it in the denominator, but I can't get away with just multiplying by the denominator without changing my expression. I have to multiply by it on the numerator and the denominator, so I'm just multiplying by 1 in a fancy form and not changing the value here. So now I do the same thing for the second rational expression. I'll write the denominator in factor form to make it easier to see what's missing from the denominator. What's missing in this denominator compared to my least common denominator is
low,
factor 2.
bro.
So I'll multiply the numerator and the denominator by 2.
Now I can rewrite everything. So the first rational expression becomes 3 times x minus 1 over 2 times x plus 1, x minus 1. And the second one becomes 5 times 2 over 2 times x plus 1, x minus 1. Now 2 times multiply out 1, or 3x plus 7 over 2 times x plus 1, x minus 1. Now 3x plus 7 doesn't factor, and there's therefore no factors that I can cancel out. So this is already reduced as much as it can be. This is my final answer. In this video, we saw how to simplify rational and multiply the denominator derivative in calculus that stretches between 2 points on the graph of the function. I'm
What the
going
hell's
to label
that?
this x value as a and this x value as b. So this point here on the graph is going to have an x value of a and a y value given by f of a. The second point will have x value b and y value f of b. Now the average rate of change for a function on the interval from a to b can be defined as the slope of the secant line between the 2 points a f of a and b f of b. In symbols, that slope m is the rise over the run, or the change in y over the change in x, which is the difference in y coordinates, f of b minus f of a, over the difference in x coordinates, b minus a. So this is the average rate of change. To put this in context, if, for example, f of x represents the height of a tree, and x represents time in years, then f of b minus f of a represents a difference in height, or the amount the tree grows, and b minus a represents a difference in years, so a time period. So this average rate of change is the amount the tree grows in a certain time period. For example, if it grows 10 inches in 2 years, that would be 10 inches per 2 years, or 5 inches per year would be its average rate of change, its average rate of growth. Let's compute the average rate of change for the function f of x equals square root of x on the interval from 1 to 4.
Oh, I got like
The average
f
rate of
equals the weight of the
change
tree.
is f of 4 minus f
This is
of
right
1
here.
over 4 minus 1. Well, f of 4 is the square root of 4, f of 1 is the square root of 1. So that's going to be 2 minus 1 over 3, or 1/3.
Hold on.
Is the square root of 4, f of 1 is the square root of 1. So that's going to be 2 minus 1 over 3, or 1/3.
Yeah, got it. F just means square root, doesn't it? Yeah. Easy.
Instead of calling these two locations on the x-axis a and b, this time I'm going to call the first location just x, and the second location x plus h. The idea is that h represents the horizontal distance between these two locations on the x-axis. In this notation, if I want to label this point on the graph of y equals f of x, it'll have an x-coordinate of x and a y-coordinate of f of x. The second point will have an x-coordinate of x plus h and a y-coordinate of f of x plus h. A difference quotient, average rate of change, equivalently between the points with coordinates x, f of
Okay,
x,
it'll be like
average rate of change could be written as f of b minus f of a over b minus, instead of b, I'm using x plus h, so I can rewrite this average rate of change as f of x plus h minus f of x over x plus h, cancel the x's, and the denominator looks like a single entity, but it still represents a difference in x values. Let's find and simplify the difference quotient for this function given. First,
wait, stop, let me do this one, let me do this one. Let me lock in chat. Let me do this. Just call this like calculus. Right. F X. We got this chat. I'll be like, simplify, you know. We got like square root x equals 2x squared minus x plus 3. That cancels out, so we have 2x plus 3. Half of that, 5x. Square root of 5. Square root of 5 equals. Answer is square root of 5.
That's f of x plus h minus I'm going to compute f of x plus h first, by shoving in x plus h everywhere I see an x in the formula for the function. It's going to give me 2 times
Holy cow. The answer is square root 5.
Notice how I use parentheses here. That's important because I need to make sure I shove in the entire x plus h for x. The entire x plus h needs to be subtracted, not just the x part. So the parentheses are mandatory.
Right,
now, I can get that f of x. And now I notice that a bunch of things cancel out. So the 2x squared and the minus 2x squared add to 0. 4xh by h.
Yeah, we just do it a different way.
Divided by h. These two, the derivative, or slope, rate of change, and the related formula, f of x plus h.
Yo, she's kind of a baddie, not gonna lie.
Minus f of x over h to
Maybe
calculate
she like hook up, do a collab.
This video will introduce the idea of limits through some graphs and examples.
Oh, snap, that's like the special K symbol. It makes. Hold up. Now, bro, Minecraft logic, holy bull knowledge. What is... Oh! Minecraft! It's that we just copied that symbol. Alright, back to learning
This video will
calculus.
introduce the idea of limits through some. Their cost $10 a pound.
I don't think I
Different
did. I
amounts.
think we skip this
Then
one.
as x is 1, f of x approaches 10. Notice that the value of f at 1 is actually equal to 0,
Bitcoin
not 10.
prices.
And so the
Holy
limit
snap.
of f of x as x goes to 1 and the
Oh my
value
gosh,
of
my
f
eyes
at
are
1
like
are not equal. This
blurry
illustrates the
eyes.
important fact that the limit here as x goes to 1 doesn't care about the value of f at 1. It only cares about the value of f when x is near 1. In general, for any function f of x, and for real numbers a and l, the limit as x goes to a of f of x equals l means that f of x gets arbitrarily close to l as x gets arbitrarily close to a. In other words, as x heads towards a, f of x heads towards l. Let me draw
No
this
more
in picture.
distractions.
In this picture, I can say that the limit as x goes to a of f of x is l, because by taking a sufficiently small interval around a of x values, I can guarantee that my y values, my f of x values, lie in an arbitrarily small interval around l. Now the limit doesn't care about f's value at exactly a, so if I change the function's value at a, or even leave the function undefined at a, the limit is still l. But the limit does care about what happens for x values on both sides of a. If, for example, the function didn't even exist for x values bigger than a, then we could no longer say that the limit was a was l. The limit would not exist. In other words,
Bro, we got it.
as minus right side values means that f of x approaches f of x.
Holy cow, bro.
Or we might choose. In this equal signs, we'll say that the limits from the right do not exist as a finite number, but they do exist as infinity and negative infinity. This video introduced the idea of limits, and one-sided limits, and infinite limits. This video gives some examples of when limits fail to exist. For this function f of x graph below, let's look at the behavior of f of x in terms of limits as x approaches negative 1, 1, and 2. Let's start with x approaching negative 1. When x approaches negative 1 from the left, the y values seem to be approaching about 1/2.
Oh snap, bro, we got like labs.
The y values seem to be approaching.
Labs chat.
So when x approaches negative 1, and we don't specify from either the left or the right, we can only say that the limit does not exist, because these two limits from the left and right are not equal.
DNA.
Now let's look at the limit as x is approaching 1. This time,
I
we approach
see
from the
like
left,
negative,
we get
positive,
a limiting y value of 2.
neutral.
We approach from the right, the y values are going towards 2. So both of these f of 1, but the limit doesn't care what happens at exactly x equals 1, just what happens when x is near 1. Finally, let's look at the limit as x goes to 2. So here on the left side, the limit is going to negative infinity, and on the right side, it's negative infinity. So we can say the limit as x goes to 2 is negative. Better answer because it carries more information. What values of x goes to 2?
No, we got like infinite. So like 2f
Limit of f of x fails to exist?
x equals negative infinite.
Well, let's see. Negative exist. Where they're vertical asymptotes.
How do you feel about ads being represented on YouTube recently? Very dissatisfied.
There's one other way that
Yo,
limits can
shit,
fail to
bro.
exist.
I think I like hacked or something.
Let's look at an example
Go
that
back
has
to
this wild
like,
behavior.
oh, so now we got like pi.
And one of the most classic examples is the limit as x goes to 0 of sine pi over x, or sometimes you'll see sine 1 over x. If you graph this on your graphing calculator and zoom in near x equals 0, you're going to see something that looks roughly like this.
This is your brain when you're struggling to focus.
Bro, I said no
This is your brain
ads.
when you're in the zone. But getting in the zone and staying there,
What the
that feels more
hell?
like luck than something you can control.
It just keeps oscillating up and down as x goes towards 0.
I got like wavelength.
0. Pi over x is getting
Amplitude.
bigger and bigger, and you're going to go through these oscillations.
Amplitude like
from one to
half.
one, faster and faster. From the other side, when x is negative, let's see something
Press, trough,
oscillating
wavelength, gamma rays,
as x goes to 0.
microwaves, radio waves. Yeah,
Also,
I did this in
start with an
physics.
example. So videos about
What's that? We're still in like
rules for function
Minecraft
fails
Special
to set up
K.
some any single value.
2.2.2? Nah, hell no, I can't be this
Is limit
deep.
infinity or negative infinity. Limit of g of x. The limit of the product of the limits. The limit of the quotient divided by 0, 9. That the limit we can use
I bet.
of x to rewrite word as x. So we can limit here plus 9. Just evaluate limit of the component functions actually exist as finite numbers. If the limit of one or both of the component functions don't exist, then the limit rules just simply don't apply. And instead, we have to use other techniques to try to evaluate the limit of a sum, difference, product, or quotient. This video is about the squeeze theorem, which is another method for finding limits. Let's start with an example. Suppose we have a function g of x. We don't know much about it, but we do know that for x values near 1, g of x is greater than or equal to 4 times the square root of x, drawn here in red, and less than or equal to 3x squared minus 4x plus
Gosh, bro,
5,
my
drawn
eyes
here
are
in
so
blue.
watery.
So on the picture, g has to lie between the red and the blue curves for x values near 1. It could look something like this. Well, what can we say about the limit of g of x as x goes to 1? Well, if you notice, the red curve and the blue curve have the exact same limit of 4 as x goes to 1. And since the green curve is squeezed in between the red and the blue curve, its limit must also be 4. This example is a special case of the squeeze theorem. Now let's say the squeeze theorem in general. Suppose that we have three functions, f of x, g of x, and h of x, and let's suppose that f of x is less than or equal to g of x, which is less than or equal to h of x, at least for x values near some number a. This inequality doesn't necessarily have to hold for x equal to a, because we're going to be talking about limits, and limits don't care what happens when x is exactly a, just when x is near a. Let's suppose also that, like in the previous example, f of x and h of x have the exact same limit as x approaches a. So we're going to suppose that the limit as x goes to a of f of x is equal to the limit as x goes to a of h of x, and we'll call this limit L. The picture looks a lot like the previous example. Again, it doesn't matter exactly what happens at x equals a. For example, g of x could have a hole there, and its value could be, for example, way up here. Since g of x is trapped here in between f of x and h of x, which both have the same limit L at a, we can conclude that the limit as x goes to a of g of x is equal to L also. And that's the squeeze theorem, also known as the pinching theorem and the sandwich theorem, three very descriptive names that capture the idea of g of x being trapped here in between lower and upper bounds. Now let's use the squeeze theorem to find the limit as x goes to 0.
Is that like sin
Now, you
cos
might remember that
10
sine 1 over x by itself
cota?
has this crazy oscillating behavior. In fact, the
Sin
limit
equals
as x
like
goes to 0 of
oh,
sine
yeah,
1
this is what I'm
over
talking
x
about,
does not
like
exist because the function never settles.
gamma
And this
waves,
equation here is between minus positive
gamma
or negative
radiation,
sign.
you know, like
Example of this
Hulk comes all
form
back
kind.
with that.
The limit of x cubed minus 1 over x squared
Yeah,
minus 5
lads.
as the next, let's look at the limit multiply minus 10
X
0
equals infinite
0 goes to 1. So I'll need
z solid.
to get the appropriate over r. Quantity r plus 3 divided by r plus 3 times 3
Oh.
all divided by r. 3 minus 3 is 0, so I can rewrite this as negative r over r plus 3 times 3. And now instead of dividing by r, which is r over 1, I can multiply by the reciprocal, 1 over r. R divided by r is 1, so this expression simplifies to negative 1 over r plus 3 times 3. So finally, I'm in a good position, because now I can just go ahead and let r go to 0, and by plugging in r equals 0, I have a limit of negative 1 over 0 plus 3 times 3, or negative 1/9. This example is a little tricky because it involves square roots, which can be hard to deal with. Well, there's one nice trick for dealing with square roots that works here, which is the conjugate. So I'm going to take the expression that we're given and multiply by the conjugate of the numerator in this case, because the numerator is the place where the square root is. By the conjugate of a minus b, I just mean a plus b. Conjugate of a plus b is a minus b. Well, of course, if I multiply on the numerator by something, I also have to multiply the denominator by the same thing, so that I won't alter the value of the expression. So this limit here is equal to the limit of the expression down here that looks more complicated, but in a moment, if we're lucky, things will clear up and become simpler. So multiplying the numerators across, I get the square root of x plus 3 squared. I get plus 2 times the square root of x plus 3, minus 2 times the square root of x plus 3, minus 4. On the denominator, I get x times the square root of x plus 3, plus 2x, minus the square root of x plus 3, minus 2. Now let's see what simplifies here. So the square root of x plus 3 squared is just x plus 3. And I see that this expression and this expression are opposite, so they subtract to 0 here. So on the numerator, I just have x plus 3, and I still have the minus 4. On the denominator looks a little messy. I'll just copy it over for now. Okay, so on my numerator, I'm getting x minus 1. Notice that when x goes to 1, that numerator is still going to 0. And in fact, as I let x go to 1, that denominator, if I plug in here, everything's going to also cancel out to 0. So I still got a 0 over 0 indeterminate form. But maybe I can use one of the previous tricks of factoring. Because look at here, if I factor an x,
Yeah, for real, bruv.
minus 1, x minus 1 on the top,
Oh,
x
gosh,
minus 1
look at me,
plus
like,
3 plus 2
chapters
denominator,
are,
indeterminate form. Anytime I see an absolute
alright,
value,
bro, we've done like
I
an
will take
hour
cases,
work in
because the
like
absolute value
17
of x plus 5
minutes.
naturally falls into cases. If x plus 5 is greater than 0, in other words, x is
Stop,
greater than
got
negative 5,
good
then the
crowd.
absolute value of this positive number is just itself. On the other hand, if x plus 5 is less than 0, in other words, x is less than negative 5, then the absolute value of a negative number is its opposite. And we make the expression x plus 5 turn it into its opposite by putting a negative sign in front. Now let's look at one-sided limits. As x goes to negative 5 from the left, we have a situation where x is less than negative 5, this situation right here. And so we can rewrite the absolute value by taking the negative of the expression. We still have a 0 over 0 indeterminate form, but if we use the old factoring trick, factor out a 2, and
Yo,
cancel,
chat, did I do it right?
we get the limit of 2 over
Wow.
negative 2. If we do the same exercise,
Alright, back to
right,
calculus.
when we're on the right, then x is greater than negative 5, so we're in this situation here, when we can just replace the absolute value with the stuff inside. And again, factoring numerator
What's
and
that?
canceling the x plus 5, we just get a limit of 2. So we have a left limit and a right limit that are different. And so in this example, the limit does not exist. So we've seen 5 different kinds of limits, all of the 0 over 0 indeterminate form. And we've used 5 different methods to evaluate them. For the first example, we used factoring. For the second example, we did the opposite of factoring. We added out. For the third example, we added together our rational expressions to simplify things. The next example, we used the old multiply by the conjugate trick. And the last example, we used cases and looked at one-sided limits. The limit law about quotients tells us that the limit of the quotient is the quotient of the limit, provided that the limits of the component functions actually exist and that the limit of the function on the denominator is not equal to 0. But what happens if the limit of the function on the denominator is equal to 0? This video will begin to answer that question. In fact, there are 2 different situations we'll want to consider. It could be that even though the limit on the denominator is equal to 0, the limit on the numerator exists and is not equal to 0. Or it could happen that both limits are 0.
I'm so hungry, bro.
First, starting with an example, and we'll look at the second situation later on. In this example,
But we
the
must
limit
stay focused.
of the numerator, negative 4x, is just negative 12, which we can see by plugging in 3 for x. But the limit as x goes to 3 of the denominator is 0. So we're exactly in one of these situations where the numerator goes to a finite non-zero number, but the denominator goes to 0. Let's see what happens as we approach 3 from the left first. As we approach 3 from the left, x is going through numbers that are slightly less than 3, numbers like 2.9, 2.99, 2.999, and so on. If we plug in those numbers into the expression here on our calculator, we're going to get answers of 116, 1,196, and 11,996. Even without a calculator, we could approximate these answers pretty closely by just thinking about the fact that since x is very close to 3, the numerator is about negative 4 times 3, so about negative 12. The denominator, 2.9 minus 3, is negative 0.1. That quotient of 2 negative numbers gives us a positive value of 120. Similarly, we could approximate the value when x is 2.99 as almost negative 12 divided by 0.01, which is 1,200, and approximate the third value as 12,000. Either way we do it, exact answers on our calculator or approximations in our head, we're noticing that these values are positive numbers that are getting larger and larger as x goes towards 3 from the left. This makes sense because if we look at our expression, as x goes towards 3 from the left, the numerator is getting close to negative 12, which is as x limit goes to 3. This answer. Like before, if we consider the signs of our numerator and denominator, we can see that as x goes to 3, our numerator is a negative number, but our denominator is a positive number since we're approaching
That's
the right
approximate,
direction,
like, so
and therefore
equals
our
to
quotient
its
is a negative number. About the limit as x goes. Another example.
Questions.
The limit as x goes to negative 4 of 5x over the absolute value of x plus 4. Notice that the limit of the numerator is just negative 20 by plugging in negative 4 for x, and the limit of the denominator is 0. Because we got an absolute value in our expression here, it's screaming out at us to look at cases. Remember that the absolute value of x plus 4 is going to equal just x plus 4 if x plus 4 is positive. In other words, if x is greater than negative 4. However, if x is less than negative 4, then the expression x plus 4 will be negative. So taking the absolute value has to switch its sign in order to make a negative expression positive. All right, so that's going to come in handy when we look at the limit as x goes to negative 4 from the left and from the right. So when we approach negative 4 from the left, x is going to be less than negative 4. So we're going to be in this situation here, where the absolute value gives us the opposite sign. That means that the limit as x goes to negative 4 minus of this expression is the same as the limit of 5x over negative x plus 4. Now, reasoning as before, as x is going to negative 4 from the left, the numerator here is a negative number, pretty close to negative 20. The denominator, since x is less than negative 4, x plus 4 is negative. The negative of it is positive. So our quotient is negative. And since the denominator is getting really tiny while the numerator is pretty level at negative 20, this limit is going to be bigger and bigger in magnitude, a limit of negative infinity. Now let's look at the limit as x goes to negative 4 from the right. In this case, x is just a little bit bigger than negative 4. So we're in this case where the absolute value doesn't change the expression. So we can rewrite this as 5x over x plus 4. Now the numerator is still going to be a negative number. The denominator, since x is slightly bigger than negative 4, slightly to the right, this expression is going to be a positive number. Negative over a positive is a negative. And again, since the denominator is getting tiny, the fraction is getting huge in magnitude, and so this limit is negative infinity. Aha! Now in this case, look at what's going on. We've got a negative infinity limit on the left and a negative infinity limit on the right. So we can conclude that the limit as x goes to negative 4 of 5x over the absolute value of x plus 4 is equal to negative infinity. In fact, we can confirm that by looking at a graph. If we check out the graph near x equals negative 4, it's going to look something like this, with a vertical asymptote at x equals negative 4, like expected. So we've seen that if the limit of f of x is equal to something that's not 0, the limit of g of x is equal to 0, then the limit of the quotient could be negative infinity, as it was in the past example. It could also be infinity, or it could just not exist. I'm supposed to say does not exist. If the one-sided limits are infinity on one side and negative infinity on the other. Now, what about this second situation that I mentioned at the beginning, when the limit of f of x is 0 and the limit of f of g of x is 0? What can we say about the limit of quotient in this situation? Well, in fact, in this situation, the limit of the quotient, it could exist and be any finite number, or infinity, or minus infinity, or it could not exist at all. In fact, in this sort of situation, which is called a 0 over 0 indeterminate form, anything could happen, which makes it, in some ways, the hardest, but in some ways, the most fun situation of all. So in another video, we'll talk about techniques for dealing with 0 over 0 indeterminate forms, and how to use algebra and other simplification techniques to evaluate these mysterious limits. So in this video, we've looked at the limits of quotients when the limit of the denominator is 0. We've done some examples when the limit of the numerator was not 0, but the limit of the denominator was 0, and we saw that these situations corresponded to vertical asymptotes and gave us an answer for the limit of the quotient of infinity, or negative infinity, or sometimes infinity on one side and negative infinity on the other. We also hinted at fun things to come when we look at the limits in this situation when the numerator and the denominator are both heading towards 0, and when anything can happen. This video is about graphs and equations of lines. Here we're given the graph of a line. We want to find the equation. One standard format for the equation of a line is y equals mx plus b. Here m represents the slope, and b represents the y-intercept, the y value where the line crosses the y-axis. The slope is equal to the rise over the run, or sometimes this is written as the change in y values over the change in x values. Or in other words, y2 minus y1 over x2 minus x1, where x1, y1 and x2, y2 are points on the line. While we could use any 2 points on the line to find the slope, it's convenient to use points where the x and y coordinates are integers, that is, points where the line passes through grid points. So here would be one convenient point to use, and here's another convenient point to use. The coordinates of the first point are 1, 2, and the next point, this is, 5, negative 1. Now I can find the slope by looking at the rise over the run. So as I go through a run of this distance, I go through a rise of that distance. It's actually going to be a negative rise or a fall because my line is pointing down. So let's see, counting off squares, this is a run of 1, 2, 3, 4 squares, and a rise of 1, 2, 3, so negative 3. So my slope is going to be negative 3 over 4. I got that answer by counting squares, but I could have also gotten it by looking at the difference in my y values over the difference in my x values. That is, I could have done negative 1 minus 2, that's from my difference in y values, and divide that by my difference in x values, which is 5 minus 1. That gives me negative 3 over 4, as before. So my m is negative 3/4. Now I need to figure out the value of b, my y-intercept. Well, I could just read it off the graph. It looks like approximately 2.75, but if I want to be more accurate, I can again use a point that has integer coordinates that I know its exact coordinates. So either this point or that point. Let's try this point. And I can start off with my equation y equals mx plus b, that is y equals negative 3/4 x plus b, and I can plug in the point 1, 2 for my x and y. So that gives me 2 equals negative 3/4 times 1 plus b. Solving for b, let's see, that's 2 equals negative 3/4 plus b. So add 3/4 to both sides, that's 2 plus 3/4 equals b. So b is 8/4 plus 3/4, which is 11/4, which is actually just what I eyeballed it to be. So now I can write out my final equation for my line, y equals negative 3/4 x plus 11/4 by plugging in for m and b. Next, let's find the equation for this horizontal line. A horizontal line has slope 0, so if we think of it as y equals
Oh my
mx
gosh,
plus b,
that bit
m
look
is 0. In other
down.
words, it's just y. And this slope intercept. Horizontal asymptote at the y value is equal to the ratio of the leading coefficients. Finally, in the third case, when the degree of the numerator is bigger than the degree of the denominator, then the numerator is getting really big compared to the denominator, so we end up with no horizontal asymptote. Finally, let's apply all these observations to one more example. Please pause the video and take a moment to find the vertical asymptotes, horizontal asymptotes, and holes for this rational function. To find the vertical asymptotes and holes, we need to look at where the denominator is 0. In fact, it's going to be handy to factor both the numerator and the denominator, since if there are any common factors, we might have a hole instead of a vertical asymptote. The numerator is pretty easy to factor. Let's see, that's 3x times x plus 1. For the denominator, I'll first factor out an x, and then I'll factor some
So
more
hungry,
using a guess and check
but I
method.
don't want to eat all my
I know
snacks.
that I'll need a 2x and an x to multiply together to the 2x squared, and I'll need a 3 and a minus 1, or else a minus 3 and a 1. Let's see if that works. If I multiply out 2x minus 1 times x plus 3, that does give me back my 2x squared plus 5x minus 3, so that checks out. Now I notice that I have a common factor of x in both the numerator and the denominator, so that's telling me I'm going to have a hole at x equals 0. In fact, I could rewrite my rational function by canceling out that common factor, and that's equivalent as long as x is not equal to 0. So the y value of my hole is what I get when I plug 0 into my simplified version. That would be 3 times 0 plus 1 over 2 times 0 minus 1 times 0 plus 3, which is 3 over negative 3 or minus 1. So my hole is at 0 minus 1. Now all the remaining places in my denominator that make my denominator 0 will give me vertical asymptotes. So I'll have a vertical asymptote when 2x minus 1 times x plus 3 equals 0, that is, when 2x minus 1 is 0 or x plus 3 is 0. In other words, when x is 1/2 or x equals negative 3. Finally, to find my horizontal asymptotes, I just need to consider the highest power term in the numerator and the denominator. That simplifies to 3 over 2x, which is bottom heavy, right? When x gets really big, this expression is going to 0. And that means that we have a horizontal asymptote at y equals 0. So we found the major features of our graph, the hole, the vertical asymptotes, and the horizontal asymptotes. Together, this would give us a framework for what the graph of our function looks like. Horizontal asymptote at y equals 0, vertical asymptotes at x equals 1/2, and x equals my program. Corresponding asymptotes of rational.
If you're a first or second year med student taking anatomy and you're feeling a little bit overwhelmed because of how much information there is to learn in such a short period of time, then you need to check out Med School Bootcamp. We have hundreds of high-yield review videos that will teach you all the basics of anatomy.
Wait, what was
Negative
that?
values, our y values don't settle down to a particular finite value. They get arbitrarily large, and so we say that the limit as x goes to minus infinity of g of x is equal to infinity. Now let's look at the graph of y equals h of x. Please pause the video for a moment and try to figure out the limit of infinity for this function. The limit as x goes to infinity of h of x is negative infinity. Because as x goes to infinity, the y values get below or more negative than any finite number. Now as x goes to negative infinity, the y values oscillate and never settle down at a particular number. So we say that the limit as x goes to minus infinity of h of x does not exist. Finally, let's look at some limits of infinity of functions without looking at their graphs first. To find the limit as x goes to infinity of 1 over x, let's think about what happens to 1 over x as x gets bigger and bigger through positive numbers. As x gets bigger and bigger, 1 over x gets smaller and smaller. So the limit as x goes to infinity of 1 over x equals 0. To find the limit of 1 over x as x goes to negative infinity, let's look at what happens as x goes through negative numbers that are larger and larger in magnitude. Now 1 over x goes through numbers that are negative, but they're still getting smaller and smaller in magnitude. So the limit as x goes to negative infinity of 1 over x is also 0. We can use similar reasoning to find the limit as x goes to infinity of 1 over x cubed. As x goes to infinity, x cubed also goes to infinity, so 1 over x cubed has to go to 0. To find the limit as x goes to infinity of 1 over the square root of x, notice that as x goes to infinity, the square root of x still goes to infinity, so 1 over the square root of x also goes to 0. In other words, both of these limits are equal to 0. Both of these examples are actually closely related because both have the form of the limit as x goes to infinity of 1 over x to the r, where r is a number greater than 0. In the second example, the square root of x is really x to the r, where r is 1/2. In fact, the limit as x goes to infinity of 1 over x to the r is always equal to 0 whenever r is bigger than 0. We can even say the same thing about the limit as x goes to negative infinity of 1 over x to the r, as long as we avoid exponents like 1/2 that don't make sense for negative numbers. But for other values of r, as x goes to negative infinity, x to the r is getting bigger and bigger in magnitude. And so 1 over x to the r is getting smaller and smaller in magnitude and heading towards 0. Notice that this is no longer true if r is less than 0. For example, something like r equals negative 2, because 1 over x to the minus 2 is really x squared, and the limit as x goes to infinity of x squared is going to be infinity, not 0. In this video, we looked at examples of limits as x goes to infinity and x goes to minus infinity. And we saw that those limits could be 0, any other number, infinity, negative infinity, or not exist. This video gives some algebraic techniques
Yeah, I
for
didn't
computing
know
the limits of
that
infinity
either.
of rational functions.
Calculus.
Let's find the limit as x goes to infinity of this rational function. The numerator and the denominator of this rational function are each getting arbitrarily large as x goes to infinity. One way to see this is by estimating the graphs. The graph of the numerator looks like a parabola pointing upwards, and the graph of the denominator looks like some kind of cubic, so something like this. For both of these graphs, as x goes to infinity, y also goes to infinity. So this is an infinity over infinity indeterminate form. And just like the 0 over 0 indeterminate forms we saw earlier, an infinity over infinity indeterminate form could turn out to be absolutely anything. So we're going to use algebra to rewrite this expression in a different form that makes it easier to evaluate. Specifically, we're going to factor out the highest power of x that we can find from the numerator and then from the denominator. In the numerator, I'm going to factor out the highest power I see in the numerator, which is x squared. When I factor x squared out of 5x squared, I get 5. When I factor x squared out of negative 4x, it's like dividing negative 4x by x squared, so I get negative 4 divided by x. You can check that this works by distributing the x squared and making sure we get back to the original expression. Now the highest power of x I see in the denominator is x cubed. So I'll factor out an x cubed from each of those terms. I get a 2 minus 11 over x plus 12 over x squared. Because factoring out an x cubed is the same as dividing each term by x cubed and then writing the x cubed on the side. Now I can rewrite again by canceling an x squared from the top into the bottom to get the limit of 1 over x times 5 minus 4 over x over 2 minus 11 over x plus 12 over x squared. Now as x goes to infinity, 4 over x goes to 0 because I'm dividing 4 by larger and larger numbers. Similarly, 11 over x goes to 0 and 12 over x squared goes to 0. So I end up with 1 over x, which is itself going to 0, times something that's going to 5 halves. So my limit is going to be 0 times 5 halves, which is just 0. I've actually been applying limit laws to do these last steps, which is fine because my component limits exist as finite numbers, something that wasn't true for my original expression when I had infinity over infinity. In this example, we're asked to find the limit as x goes to negative infinity of a different rational expression. I encourage you to stop the video and try it for yourself first. In this example, the highest power of x in the numerator is x cubed, and the highest power in the denominator is also x cubed. Factoring out the x cubed from the numerator, we get x cubed times 3 plus 6 over x plus 10 over x squared plus 2 over x cubed. And factoring out the x cubed from the denominator, we get x cubed times 2 plus 1 over x plus 5 over x cubed. Now the x cubes cancel, and all these parts go to 0. So when the dust clears here, our limit is just 3 halves. In this next example, the highest power in the numerator is x to the fourth, and the highest power in the denominator is x squared. So we factor out the x to the fourth from the numerator, and the x squared from the denominator, and cancel as much as we can. A lot of these pieces are going to 0, so our limit is the same as the limit of x squared times 1 over negative 5. As x goes to negative infinity, x squared is positive and goes towards positive infinity. Multiplying by negative a fifth turns it negative, but doesn't change the fact that the magnitudes are getting arbitrarily large. Therefore, our final limit is negative infinity. Now let's look at these same 3 examples again more informally, using a heuristic to get the same conclusions. In the first example, the term 5x squared dominates the numerator because x squared is much larger than x when x is large. In the denominator, the highest power of x, 2x cubed, dominates because x cubed is much larger than x squared, or x, when x is large. If we ignore all the other terms in the numerator and denominator and just focus on the important terms, which have the highest powers, then we can rewrite our limit as the limit of 5x squared over 2x cubed, which is the same as the limit as x goes to infinity of 5 over 2x, just by canceling x's, which is 0 as x goes to infinity.
What's the
Similarly, if we just focus on the highest power
the
term in the
audio?
numerator and denominator in the second example,
My
we get the
microphone
limit
did.
of 3x cubed over 2x cubed, which simplifies to the
Mic's
limit
not plugged in.
of 3 halves, which is just 3 halves. In the third example, the highest power terms are x to the fourth and negative 5x squared, and we rewrite the limit using only these highest power terms and simplify, and we get the limit as x goes to negative infinity of x squared over negative 5, which is negative infinity, as before. For rational functions in general, looking at the highest power terms lets you reliably predict the limits of infinity and negative infinity. When the degree of the numerator is less than the degree of the denominator, then the limit as x goes to infinity or negative infinity is 0, as in example 1 above. When the degree of the numerator is equal to the degree of the denominator, then the limit is just the quotient of the highest power terms, which is how we got 3 halves as the limit in the second example. And finally, if the degree of the numerator is greater than the degree of the denominator, then the limit is going to be plus or minus infinity, like it was in the third example. These shortcut rules are really handy, but it's important to also understand the technique of factoring out highest power terms, since this technique can be used more generally. This video gave 2 methods for computing limits of infinity of rational functions. First, there's the formal method of factoring out highest power terms and simplifying. Second, there's the informal method of looking at the degree of the numerator and the degree of the denominator and focusing on the highest power terms. In the past, you may have heard an informal definition of continuity.
Hello.
Something like a function is continuous
My
if you can draw it
name's
without ever changing the function.
Jeffrey.
In this video, we'll develop a more precise definition of continuity based on limits. It can be helpful to look at some examples of functions that are discontinuous, that is, functions that fail to be continuous, in order to better understand what it means to be continuous. Please pause this video and try to draw.
Oh yeah, I paused the video. Alright, we're gonna test just the mic with the mic.
This is the mic without it, and yeah, my voice sounds chopped because I'm sick.
Graphs of at least 2 different functions that fail to be continuous in different ways. One common kind of discontinuity
My
is
voice
called a jump
sounds
discontinuity.
chopped because I'm sick.
A function has a jump discontinuity whose graph separates into two pieces with a jump between them.
with the
This particular function can be described as a
This
piecewise
is
defined
the
function
mic
with 2 linear
without
equations.
it, and
f of x
yeah.
equals 2x,
The
when
voice
x is
sounds
less than or equal to
chopped
1,
because
and
I'm
f of x
sick.
equals negative x plus 2.
Mic.
Alright, we're
when
gonna
x is greater
test.
than. Another common kind of discontinuity is called a removable
Oh yeah, I
discontinuity.
paused the video. Alright,
You
we're
know
gonna
the concept
test
before
just
when
the
you learn about
mic
rational functions
with
with
the
whole.
mic.
For example,
Yeah, I
the
paused
function
the video.
f of x
Alright, we're gonna
equals
test
x minus 3 squared times x minus 4 divided by x minus 4, which has a whole when x equals 4 and otherwise looks like the graph of x minus 3 squared. This kind of discontinuity is called removable because you could get rid of it by plugging the hole, just by defining f to have an appropriate value when x equals 4. So in this case, you want f of x to be the same when x is not equal to 4, but you want it to have the value of 1 when x equals 4, and that would amount to plugging the hole and making it continuous. In this original example, our function had a removable discontinuity because it wasn't defined when x equals 4. But a function could also have a removable discontinuity because it's defined in the wrong place at x equals 4. For example, too high or too low to fit the trend of f. A discontinuity can also occur at a vertical asymptote, where it's called an infinite discontinuity. For example, the rational function g of x is 1 over x minus 2 has an infinite discontinuity at x equals 2. Occasionally, you may encounter discontinuities that don't look like any of these. For example, the graph of the function y equals cosine of 1 over x has a wild discontinuity at x equals 0 because of the wild oscillating behavior there. So for a function to be continuous at x equals a, we needed to avoid all of these problems. To avoid a jump discontinuity, we can insist that the function's limit has to exist at x equals a. To avoid a whole or removable discontinuity, we can insist that f has to be defined at x equals a. To avoid the other kind of removable discontinuity, in which f of a is defined, but it's in the wrong place, we can insist that the limit of f of x as x goes to a has to equal f of a. Sometimes the definition of continuity is written with just the third condition, and the first 2 conditions are implied. Notice that these 3 conditions not only exclude jump discontinuities and removable discontinuities, they also exclude infinite discontinuities and wild discontinuities. For example, in our third example, the function can't be continuous at x equals 2 because it fails to have a limit at x equals 2 and it fails to have a value at x equals 2. In our wild discontinuity example, the limit also fails to exist at x equals 0, so the function can't be continuous there. So what are all the places where this function f is not continuous and why? Please take a moment to think about it for yourself. The function is not continuous at negative 3 because the function is simply not defined there. The function is not continuous at x equals 1 because of that jump discontinuity. In the language of limits, we say that the limit of f of x does not exist. When x equals 2, the limit of the function exists and equals 3, but the value of the function is down here at negative 1. So the function is not continuous because the limit doesn't equal the value. At x equals 3, the function is not continuous because, once again, the limit doesn't exist. Notice that at x equals negative 2, even though the function turns a corner, the function is still continuous because the limit exists and equals 2, and the value of the function is also 2. The function drawn here is not continuous at x equals negative 2 because the limit doesn't exist at x equals negative 2. The limit from the left is 1, while the limit from the right is 0. But it is true that the value of the function
Say something in chat right
is
now.
equal to the limit of the function from the left side.
Can you guys hear that?
That is, f of negative 2 is equal to the limit as x goes to negative 2 from the left of f of x.
f of negative 2 is equal to
Notice
the
that we
limit
can't say the
as
same
x
thing
goes to
about the
negative 2
right
from the
limit.
left
The
of
limit from the
x.
right is 0, while the
But
value
it
of
is
the
true
function
that
is
the
1.
value of
And
the
the
Say
value
something in
in
chat
this
right
situation,
now.
we say that f is continuous from the left and
Nah,
from the right, and from the right.
sure, mother, dad. We're just gonna, you know.
N is a number between f of a and f of b, then there has to be a number c in the interval AB such that f of c equals n. In our example, there are 3 such possible values for c. It could be right here, since f of that number equals n, or it could be here or here. I'll just mark the middle one. The intermediate value theorem can only be applied to continuous functions. If the function is not continuous, then it might jump over n and never achieve that value. One application of the intermediate value theorem is to prove the existence of roots or zeros of equations. Recall that a real root of p of x is a real number c such that p of c is 0. We're going to want to apply the intermediate value theorem with n equal to 0. Our polynomial is defined on the whole real line, not just an interval. But the trick here is to pick an interval AB so that p of a is negative and p of b is positive, or vice versa, so that the intermediate value theorem will tell us that p has to pass through 0 in between. I'm just going to use trial and error here and calculate a few values of p. So p of 0 is easy to calculate. P of 0 is just 7. P of 1 is going to be 5 minus 3 minus 12 plus 7, which equals negative 3. So in this very lucky example, the first 2 numbers that we pick will work for our a and b. So we can just let ab equal 0, 1, because p of 0 is a positive number and p of 1 is a negative number. So actually the graph should look a little different. The graph looks more like this. But in any case, by the intermediate value theorem, there has to be a number c in between, in this case, 0 and 1, where our polynomial p achieves this intermediate value of 0. And that number c, we don't know what it is, but we know it's somewhere in the interval 0 to 1. That value c gives us a real root for our polynomial. There may be other real roots, but we've proved there exists at least one. The intermediate value theorem has lots of other applications besides finding roots. For example, suppose you have a wall that runs in a circle around a castle, and the height of the wall varies continuously as a function of the angle. Surprisingly, the intermediate value theorem can be used to show there must be somewhere 2 diametrically opposite places on the wall with exactly the same height. See if you can figure out a way to show this. In this video, we stated the intermediate value theorem, which holds for continuous functions, and talked about a couple of applications. This video introduces the trig functions sine, cosine, tangent, secant, cosecant, and cotangent for right triangles. For a right triangle with sides of length a, b, and c and an angle theta as drawn, we define sine of theta as the length of the opposite side over the hypotenuse. The side that's opposite to our angle theta has measure a, and the hypotenuse is this side here with measure c, so that would be a over c for this triangle. Cosine of theta is defined as the length of the adjacent side over the length of the hypotenuse. This side here is the side adjacent to theta. Of course, the hypotenuse is also adjacent to theta, but it's special as the hypotenuse, so we don't think of it as the adjacent side. So that would be b over c. Tangent of theta is the opposite side length over the adjacent side length, so that would be a over b. The mnemonic to remember this is SOHCAHTOA. That's sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. In fact, there's a relationship between tangent and sine and cosine. Namely, tangent of theta is equal to sine of theta over cosine of theta. If you want to see why, that's because sine of theta over cosine of theta is given by sine, which is opposite over hypotenuse, divided by cosine, which is adjacent over hypotenuse. If we compute these fractions by flipping and multiplying, the hypotenuse length cancels, and we just get opposite over adjacent, which is by definition tangent of theta. There are 3 more trig functions that are defined in terms of sine, cosine, and tangent. First of all, there's secant of theta. By definition, that's 1 over cosine of theta. So it's going to be 1 over the adjacent over the hypotenuse, which is the hypotenuse over the adjacent, which in this triangle is c over b. Cosecant of theta is defined as 1 over sine theta. So that's 1 over the opposite over the hypotenuse, which is the hypotenuse over the opposite, and for this triangle, that's going to be c over a. Finally, cotangent of theta is defined as 1 over tan theta. So that's going to be 1 over opposite over adjacent. Flip and multiply, I get adjacent over opposite, which in this case is b over a. So notice that the values for cotangent, cosecant, and secant are the reciprocals of the values for tangent, sine, and cosine, respectively. Let's use these definitions to find the exact values of all 6 trig functions for the angle theta in this triangle. I'll start with sine of theta.
The
that's
3
opposite over
people.
hypotenuse. Well, for this angle theta,
Probably
the opposite
me.
side is down here and has measure 2.
Awesome.
The hypotenuse has measure 5.
And
So sine theta is 2 over 5.
learning
Cosine theta is
calculus.
adjacent over hypotenuse, but I don't know the value of this side length. But fortunately, I can find it using the Pythagorean theorem. Since I have a right triangle here, I know that a squared, I'll call this side length a, plus b squared, where b is this other leg of the triangle, is equal to c squared, where c is the hypotenuse. So here I have a squared plus 2 squared equals 5 squared, which means that a squared plus 4 equals 25. A squared is 21, so a is plus or minus the square root of 21. But since I'm talking about the length of a side of a triangle, I can just use the positive answer. Returning to my computation of cosine theta, I can write it as adjacent, which is the square root of 21, over hypotenuse, which is 5. Tangent theta is the opposite over the adjacent, so that's going to be 2 over the square root of 21. To compute secant of theta, that's 1 over cosine theta, so that's going to be 1 over square root of 21 over 5, which is 5 over the square root of 21, the reciprocal of my cosine value. Cosecant theta is 1 over sine theta, that's going to be the reciprocal of my sine, so 5 halves. And cotangent theta is 1 over tan theta, so it's going to be the reciprocal of my tan value, square root of 21 over 2. Finally, we'll do an application. So if we have a kite that's flying at an angle of elevation, that's the angle from the horizontal, of 75 degrees, with a kite length string of 100 meters, we want to find out how high it is. I'll call the height y. Well, we want to relate the known quantities, this angle and this hypotenuse, to the unknown quantity. The unknown quantity is the opposite side of our triangle. So if we use sine of theta equals opposite over hypotenuse, then we can relate these known amounts, sine of 75 degrees, to our unknown amount, y, which is the opposite, and our known amount of 100 meters. Solving for y, this gives that y is 100 meters times sine of 75 degrees. We can use a calculator to compute sine of 75 degrees. Be sure you use degree mode and not radian mode when you type in the 75. When I do the computation, I get a final one.
If you're running your own business, you need Symphony. Just tell it what's on your plate, and it jumps right in, analyzing ways to move your business forward and gathering the right
length of the opposite side over the length of the hypotenuse. But if we use this method to try to compute sine of 120 degrees, things go horribly wrong. When we draw this 120 degree angle and this right angle, there's no way to complete this picture to get a right triangle. So instead, we're going to use a unit circle, that is, a circle of radius 1. The figure below illustrates how right triangles and the unit circle are related. If you draw right triangles with larger of hypotenuse 1, with larger and larger angles, then the top vertex sweeps out part of a unit circle. Let's look at this relationship in more detail. In this figure, I've drawn a right triangle inside a unit circle. The hypotenuse of the triangle is the radius of the circle, which is 1. One vertex of the right triangle is at the origin, another vertex of the right triangle is at the edge of the circle. I'm going to call the coordinates of that vertex A, B. Now the base of this right triangle has length A, the x-coordinate, and the height of the right triangle is B, the y-coordinate. If I use the right triangle definition of sine and cosine of theta, this right here is the angle theta, then cosine of theta is adjacent over hypotenuse. So that's A over 1, or A. Notice that A also represents the x-coordinate of this point on the unit circle at angle theta from the x-axis. I'll write that down. For sine of theta, if I use the right triangle definition, that's opposite over hypotenuse on the unit circle.
What's that like? A bagel?
Degrees minus 60 degrees, which is the same thing as sine of minus 60 degrees. Thinking about the unit circle, minus 60 degrees means I start at the positive x-axis and go clockwise by 60 degrees. That lands me about right here, and so that's one of the special angles that has an x-coordinate of 1/2, a y-coordinate of negative root 3 over 2.
Three people watching, this might my work be out, you know?
The next property I call the even
Learning
property. It
calculus.
says that cosine is an even
It's
function.
all like below me,
Cosine of
you
negative
know?
theta is the same thing as cosine of theta.
Just thought to go back to the
While sine is
basics.
an odd function, which means that sine of negative theta is a negative of sine of theta. To see why this is true, let's look at an angle theta and the angle negative theta. A negative angle means you go in the clockwise instead of counterclockwise direction from the positive x-axis. The coordinates of this point, by definition, are cosine theta, sine theta, whereas the coordinates of this point are cosine negative theta, sine of negative theta. But by symmetry, these 2 points have the exact same x-coordinate, and therefore positive and this one's negative. That means we can write sine of x as equal to cosine of x minus pi over 2, since subtracting pi over 2 on the inside shifts the cosine graph to the right by pi over 2. Next, let's look at domain and range. The domain of sine and cosine is all real numbers. I'll write that as negative. The input values for the domain range, that is the actual values of sine and cosine, given an odd behavior, origin, and must be odd. We can also use the maximum and minimum points. Here, the midline is y equals 0. The amplitude is the vertical distance between a maximum point and the midline. You can also think of the amplitude as the vertical distance between a minimum point and the midline, or as half the vertical distance between a min point. Scalar horizontal intervals is 2 pi, or minimum points, plus 2 pi. In this video, we graphed y equals cosine of x and y equals sine of x, and observed that they both have a midline at y equals 0, an amplitude of 1, and a period of 2 pi. Sinusoidal functions are functions that are related to sine and cosine by transformations, like stretching and shrinking and shifting. This video is about graphing these functions. Let's start by graphing the function y equals 3 sine of 2x. This function is related to the function y equals sine x, so I'll graph that first. Now the 3 on the outside stretches this graph vertically by a factor of 3, while the 2 on the inside compresses it horizontally by a factor of 1/2. If instead I want to graph y equals 3 sine 2x plus x and a period shrinks every half times 2, it affects the sine at y equals distance between only affects this function, given the g of x of f of x, or 2x, graph the function, I could just do x. And to graph this, look at of x, and our final transformed function, y equals 3 sine of 2 times quantity x minus pi over 4 minus 1. Our original sine function has midline at y equals 0, amplitude of 1, and period of 2 pi. For our transformed function, the 3 on the outside stretches vertically, so it makes the amplitude 3. The minus 1 on the outside shifts everything down by 1, so it brings the midline, y equals 0, down to y equals negative 1. The 2 on the inside shrinks everything horizontally by a factor of 1/2, so the period becomes 1/2 times 2 pi, which is pi. Finally, there's a horizontal shift going on. Our transformed function shifts to the right by pi over 4. This horizontal shift is sometimes called the phase shift. The function we just analyzed was y equals 3 sine 2 x minus pi over 4. This makes a lot of sense because tangent of x is sine of x over cosine of x. And so you're going to get x-intercepts. That's where y is 0, which is where the numerator is 0. And sine x is 0 at values of the form pi, 2 pi, and so on. From the graph, you can see the vertical asymptotes are at values like negative 3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2. These values can be written as pi over 2 times k where k is an odd integer. Again, this makes sense from the definition of tangent, since vertical asymptotes will occur where the denominator is 0 and cosine x is 0 at numbers like negative pi over 2, pi over 2, 3 pi over 2, and so on. The domain of tangent is the x-axis for which it's defined, so that's going to be everything except for the vertical asymptotes. We can write that as x such that x is not equal to pi over 2 times k for k, an odd integer. The range, or the y values, go all the way from negative infinity to infinity, and the period, as we mentioned previously, is pi, since the smallest repeating unit has a horizontal width of pi. To graph y equals secant x, I'm going to remember that secant is 1 over cosine. So if I start with a graph of cosine, I can take the reciprocal of the y values to get the graph of secant. The reciprocal of 1 is 1. The reciprocal of 0 is undefined, so I'm not going to have a value at pi over 2, negative pi over 2, 3 pi over 2, or negative 3 pi over 2. When I take the reciprocal of numbers just less than 1, I'm going to get numbers just greater than 1. But if I take the reciprocal of positive numbers getting close to 0, I'm going to get really big positive numbers going up towards infinity. Similarly, on the other side, over here, I have numbers close to 0 but negative, so their reciprocals will be negative numbers heading towards negative infinity. The reciprocal of negative 1 is negative 1, and similarly here. So I'm getting kind of positive and negative buckets and upside down buckets as the graph of my secant. Notice that secant has a period of 2 pi, which makes sense since cosine has a period of 2 pi. It has a range that goes from negative infinity to negative 1 inclusive, and from 1 to infinity. That makes sense because the range of cosine is between 1 and negative 1, and we're taking the reciprocal of those values. The domain is everything except for the vertical asymptotes. Now the vertical asymptotes are where cosine is 0. So that is at values of the form pi over 2, 3 pi over 2, etc. That's values of the form pi over 2 k, where k is an odd integer. So the domain is going to be x values such that x is not equal to pi over 2k for k, an odd integer. The x-intercepts of secant, well, it doesn't have any, because you can't take 1 over something and get the number 0 for your y value.
Oh snaps, we got like
Graph of y equals tan x.
weird
And y
patterns of
equals
crap.
secant x.
Yeah,
This is the graph of y
calculus
equals
is so
cosecant x.
like,
It looks similar to the graph of tangent x. It's just a decreasing
you
function instead
know,
of an increasing one, and it has its vertical asymptotes and its x-intercepts in different places.
Cartesian plane.
Finally, this green graph is the graph of
Oh,
y equals
Cartesian
cosecant x.
plane.
It's related to the graph of sine x, since cosecant is 1 over sine x. In fact, if I draw the graph of sine x in between, you can see how it kind of bounces off because it's the reciprocal. I encourage you to memorize the general shape of these graphs. You can always figure out the details by thinking about how they're related to the graphs of cosine of x and sine x. This video is an introduction to solving trig equations. Let's start with the equation 2 cosine x plus 1 equals 0. I want to find all the solutions in the interval from 0 to 2 pi, and then get a general formula for all solutions, not just those in that interval. Let me start by rewriting this equation to isolate the tricky part, which is cosine of x. So I'm going to write 2 cosine x equals negative 1, and then divide both sides by 2. Now I'm looking for the angles x between 0 and 2 pi, whose cosine is negative 1/2. Since negative 1/2 is one of the special values
Got
of the
it!
circle,
I got the answer! Yo, what the hell is that? Gently,
0
like,
to 2 pi must be either 2 pi over 3 or 4 pi over 3. My answer needs to include both of these values. There are no other spots on the unit circle whose cosine is negative 1/2, but there are more angles because we can always take one of these angles and add multiples of 2 pi to it. So if I want to find all solutions, I can take these two principal solutions, 2 pi over 3 and 4 pi over 3, and simply add multiples of 2 pi to them. For example, 2 pi over 3 plus 2 pi, or 2 pi over 3 minus 2 pi, 2 pi over 3 plus 4 pi, and so on. A much more efficient way to write this is to write 2 pi over 3 plus 2 pi times k, for k, any integer. That is, any positive or negative whole number or 0. Similarly, I can write 4 pi over 3 plus 2 pi k to capture all solutions based on the principal solution 4 pi over 3 by adding and subtracting multiples of 2 pi. This is my final solution.
wait, look at that!
As
Cartesian
usual, I'm going to start out by
plane
cleaning things
type
up and
crap.
isolating the tricky part, which in this case is tangent.
Yo,
To
Major!
both sides, that'll give me 3 tan x equals the square root of 3, and so tan x is the square root of 3 over 3. The square root of 3 over 3 looks suspiciously similar to the value of square root of 3 over 2, which is a special value on my unit circle. So my suspicion is that my unit circle will again help me find this value of x without a calculator. Recall that tan x is sine x over cosine x. So I'm looking for angles on the unit circle between 0 and 2 pi, where the ratio of sine over cosine will give me square root of 3 over 3. I actually only need to look in the first quadrant and the third quadrant, because those are the quadrants where tangent is positive. And I really only need to look at angles whose either sine or cosine has a square root of 3 in it. So by trial and error, I can see that tan pi over 6, which is sine pi over 6 over cosine pi over 6, will give me 1/2 over root 3 over 2. That's the same thing as 1/2 times 2 over root 3, which is 1 over root 3. If I rationalize that, I get root 3 over 3. So that value works. If I try tan of pi over 3 instead, I get root 3, which is not equal to root 3 over 3. So pi over 3 doesn't work. Similarly, I can work out the values in the third quadrant and see that 7 pi over 6 works, but 4 pi over 3 does not. So my answer to part A includes just the two values, pi over 6.
Yo, chat, I figured it out.
Now, if I want to find all solutions, not
Yeah,
just
we
those
got
in the interval from 0 to 2 pi,
compass.
I notice that I can take one of these principal solutions and add multiples of 2 pi to it, because that'll give me the same angle. So I get pi over 6 plus 2 pi k, and 7 pi over 6 plus 2 pi k for k, any integer. This is a correct answer, but it's not as simple as it could be. notice that 7 pi over 6 over here on the unit circle is exactly pi more than pi over 6. So instead of taking both of these and adding multiples of 2 pi to them, I could get all the same answers by just taking one of them and adding multiples of pi to it. So a more efficient answer is to say that x equals pi over 6 plus pi times k for k any integer. This will still
Square root
all
of
these
like
solutions, because when k is
2
even,
of
I'll get this family of solutions,
2.
and when k is odd, I'll get this family. For
Square
example,
root
when k
of
is 1,
2.
pi over 6 plus 1 times pi is just the original 7 pi over 6. If you think about the fact
That's
that tangent
actually
has a period of
1.
pi,
0
instead of 2 pi,
chap.
it makes
Figured
more
it
sense to be able
out.
to write the solutions in this form. In this video,
Ugh.
we solve basic tricky
Go.
problems
The baddie's
by
back on screen.
isolating sine or tangent, or the same thing would work with cosine.
Yo,
And then,
date me baddie,
using the
bro.
unit circle, to find principal solutions.
I didn't know
Principal solutions
calculus
are the
had
solutions
such cuties.
between 0 and 2 pi. And then adding
Oh, yeah.
multiples
Trig.
solutions.
Studying computer science at SAE is nothing like your traditional uni. There are no huge lecture theatres full of people who'd rather be somewhere else.
X, but actually here f of x equals x squared.
Oh, yep, like
I also
F.
have a tangent line to my function drawn in red. This tangent line is the tangent line at the point 1.5, 2.25.
Like-
By a tangent line, I mean a line that touches the graph of my function at this one point and heads off in the same direction as the function. Well, normally to compute a slope, we need 2 points. But for the tangent line, we really only have the exact coordinates of this one point. We could approximate the slope by guessing the coordinates of some other point on that line. But in the long run, we'll end up with a more accurate estimate if we do something else. So what we're going to do instead is we're going to calculate the slope of a secant line. A secant line is a line that goes through
Look
2
at that
points on my
chat.
graph.
Figuring it
So
out.
in this case, my secant line is going through my original point and this other point at x equals 3. So that's the point 3, 3 squared, 3, 9. Okay, so here's my secant line. To calculate the slope of my secant line, I use the fact that slope is rise over run, or in other words, it's the change in y over the change in x, and that's going to be written in function notation. F of 3 minus f of 1.5 is giving me the change in y, and 3 minus 1.5 gives me the change in x. Well, since f of x is x squared, it's the same thing as 3 squared
yeah,
minus
yeah.
1.5 squared over 3 minus 1.5, so that's just 9 minus 2.25 over 1.5,
Right,
which ends up as 4.5. So 4.5 is the slope of the secant line.
Equivalent.
Well, the idea here is that the slope of my secant line is an approximation of the slope of my tangent line. But in this example, really the secant line that I've used, its slope is only a very rough approximation of the tangent line, not very accurate at all. So how could I get a better approximation of the slope of my tangent line? Well, one thing I could do is I could use as my second point, instead of using this point way out here, I could use a point closer to my first point. So for example, I could use the point 2, f of 2, in other words, the point 2, 4, as my second point for my secant line. So let me draw that, and let me calculate its slope, which after some arithmetic is going to give me an answer of 3.5.
Oh, yeah, triangle.
Well, I can continue to pick second points for my secant line closer and closer to my first point, and I should end up with more and more accurate approximations of my tangent line. Let me make a little chart for this.
Okay.
For my next secant line, I could take my second point something pretty close to 1.5, say 1.6, and after some arithmetic, I get a slope of 3.1. I could take my second point to be 1.51, that's going to give me a slope of 3.01, and so on. To write this more generally, if I take my second point as x,
Oh, yeah, we
then
need
the
a
slope of my
table.
secant line is going to be given by, again, the rise of the run, so that's going to be f of x minus f of 1.5 divided by x minus 1.5. Change in y over the change in x. That's my slope. Now, there's no reason I necessarily have to take my second point to be on the right side of my first point. I could be using instead points on the left side here. Continuing with my chart, letting my second point be 1, I can do the same computations to get a slope of a secant line of 2.5 here. I could get even closer on the left, say something like 1.4, and get a slope of 2.9, and so on in general. If I have a point x, f of x, and I use the secant
yeah,
line through that point and
infinite-
another point, I calculate the slope
infinite
as
positive
change in y over change
Infinity
in x, which is
to
going
the power of
be
negative 2
at its own
equals
name,
neutral
it's called the derivative
1.
of f of x at x
Right,
equals
like,
1.5.
first
In other
rule
words, the derivative, which is
calculus,
written
you know,
as
like,
f prime at
try
1.5, is the limit as x goes to 1.5
One.
of f of x minus f of 1.5
And
over x minus 1.5.
object
Now, based on our numerical tables,
will
for example here, we can see that that limit
remain
seems to be heading towards 3, whether x approaches
in
1.5 from the right or from the left. So
motion
I'll write down the answer of 3.
unless
You know, numerical evidence is pretty strong. If we wanted to have a really
active.
precise argument, we actually need to use algebra to compute this limit exactly using the formula for the function itself, f of x equals x squared. And we'll do examples like that in a future video. But for now, the derivative at 1.5 was
Oh,
given
yeah,
by the limit as x
probable
goes to 1.5 of f of x minus f of 1.5
x cubed
divided by x minus 1.5.
h
Well, in general,
k
the derivative of function y equals f of x at an x value a
69
is given by f prime of a equals the limit as x goes to a of f of x minus f of a over x minus a. The function is said to be differentiable at a if this limit exists. In particular, both the limit from the left and the limit from the right have to exist and be equal for the function to be differentiable at x equals a. There's another
Intense
equivalent version of
stuff,
the
not
definition of
gonna lie.
derivative that's very common and very useful. If we're looking at the graph of a function, I'm trying to calculate the slope of the secant line between the points a, f of a, and x, f of x. Then let's introduce the letter h to be the quantity x minus a. So h represents the run when I'm counting h at 0.
Oh yeah, they
a
had like
over h.
lime.
One way to think of this is that we're just
Maybe
relabeling this point right
infinity.
here as the point a plus h, f of a plus h. And the slope of the tangent line is still the limit of the rise over the run as the run goes to 0. This is the definition of derivative that we'll use most frequently going forward when we actually calculate derivatives based on the definition in future videos. But for now, let's look at some examples to practice recognizing the derivative rather than computing it. So each of these following two expressions is supposed to represent the
See,
derivative.
I'm telling you, bro, I predicted
For
it.
each example, we're going to find the function and
3,
figure out the
2
Now remember, we've got two
plus
definitions of
h.
derivative going on. They're both equivalent, but they look different. One of them looks like derivative of f at a is the limit as x goes to a of f of x minus f of a over x minus a. And the other version is the limit as h goes to 0 of f of a plus h minus f of a over h. Now, you might notice that our first expression looks more like this first definition, because x is going to some number that's not 0, and we have both x and a number in the denominator here. Whereas our second expression looks more like the second definition. We've got the h going to 0, and we just got the h on the denominator here. Okay, so let's look at this first one here. First, let's figure out what a is here. It seems like a has got to be negative 1, since x is approaching negative 1.
Yeah,
that
I'm
makes
telling
sense,
you,
because now
like
here on the denominator,
F1.
x plus 1 could be thought of as x minus negative 1. So that's our x minus a, with a is negative 1. Okay, great. So we've got a. Now we need to find f, and we need the numerator here to look like f of x minus f of a. Well, let's just try, and we've got our, now this is 8, and see a is f, it's all fair, f with a tangent. We'll continue with some using the limit of f of a plus, find the derivative of f of x, which
Yeah,
is
I'll
1
tell
over
you,
the square root of 3 minus
square
x,
root
at x
3.
equals negative 1. Well, in other words, we want to find f prime of negative 1, so that's the limit, as h goes to 0, of f of negative 1 plus h minus f of negative 1 over h. Using our definition of f, that's the limit of 1 over
This
the
is
square root
intense
of 3
stuff, you
minus
know.
negative 1 plus h minus 1 over the square root of 3 minus negative 1 all over h. Let me clean this up a bit. So this is 1 over the square root of, let's see, it's 3 minus negative 1, so that's 3 plus 1 or 4 minus h minus 1 over the square root of 4 over h. And I guess I can replace the square root of 4 with 2. Now, unfortunately, I can't just evaluate this by plugging in h equals 0, because if I try that, I get one of
Yeah,
these
guys,
zero
this
indeterminate
is how
slopes.
it's going.
Remember, these a lot when calculating derivatives by definition. It kind of makes sense, because remember the context we're
Yeah,
computing
like,
slopes of
I
seeking
worked
lines.
out, like, oh yeah, like
Closer to
0
each other, so our
over
rise and our
0,
lines are both going to
like
0.
y
So it
or
makes sense we'll get the
something.
0 over 0. It's going to denominator for my tricks. I have
Negative
times h
10
squared
is that
plus h cubed. I'm getting this from the formula for multiplying out a cubic, which I've memorized, but you can also get it more slowly just by writing out 2 plus h times itself 3 times and distributing. Now I need to subtract 3 times 2 and 3 times h. And finally, I need to subtract my 2 cubed and then add my 3 times 2, all this over h.
2,
Now, a few of my terms cancel out to 0 here. 2 cubed minus 2 cubed. And let's see, I've got a minus 3 times 2 and a plus 3 times 2. And I notice all the terms that are left have
sneeze.
h's in them. So I'm going to factor out an h from the top for the remaining terms here. And that gives me, let's see, 3 times 2 squared, so that's 12 plus 6h plus h squared minus 3 over h. Now, h divided by h is 1, so I'm just left with the limit as h goes to 0 of 12 plus 6h plus h squared minus 3. As h goes to 0, I can just plug in h 0 and I get 12 minus 3, which is 9. So my slope of my tangent line, my derivative, is 9. Now, I'm not quite done. I still need to find the equation of the tangent line. I just know that its slope is 9. So the equation of the tangent line, the equation of any line, is something like y equals mx plus b, and here m is 9. Point or 2. Now, using the derivative of a function,
It's
y equals
like
f of x.
good here. Oh, yeah, that's special K.
EVE
Full of
Online
that.
is a vast universe,
Minecraft.
alive with the unrelenting activity and combined history of its players. Pursuing lives of adventure.
Oh snap, this
This video
space
is
and
about two limits
calculus.
involving trig functions that
Oh,
turn out to be very
Milky
useful.
Way.
Namely, the limit as theta goes to 0 of sine theta over theta, and the limit as theta goes to 0 of cosine theta minus 1 over theta. These limits turn out to have really nice simple answers, as long as we keep theta in radians,
Right,
not
my
degrees.
cause.
Let's consider the limit on the left
Angle.
first. That's the limit as theta goes to
Oh,
0
stop.
of sine theta
Go right down.
for theta. Notice that we can't just evaluate this limit by plugging in 0 for theta, because as theta goes to 0, sine theta in the numerator also goes to 0, and theta itself goes to 0, so we end up with a 0 over 0 derivative form. We can, however, build up some evidence of what this limit might be by using a calculator and a table of values, or by looking at a graph. So here's the theta axis, and here's the y-axis. And you can see that as theta goes to 0 from either the right or the left, it's looking like the y value is going to 1. The second limit here on the right is also a 0 over 0 determinate form. Since as theta goes to 0, cosine theta goes to 1, so cosine theta minus 1 goes to 0. But again, looking at the graph, we have some evidence to suggest that as theta goes to 0, our expression is also going to 0. These graphs provide strong evidence, but graphs can be misleading, and they're no substitute for a rigorous proof. So for a pretty cool geometric and algebraic proof of these facts, please see the proof video for this section.
Oh
The
yeah.
fact that the limit as theta goes to 0
One
of sine
does
theta
not
over
equal
theta is 1 is
infinity.
really handy when you want to approximate sine theta.
We're
Because in
learning.
theory, this is saying that
We're
sine theta
learning.
is approximately equal to theta
It's
itself
like,
when theta is near 0,
it's my work,
because
you
the
know.
ratio is approximately 1. So if I want
I'll
to approximate
start. We'll
sine
level
of this value of theta
X,
without a calculator,
Y.
I can use that fact and say that the sine of
Well,
0.01769 is going to be approximately equal to 0.01769. This is an important time to remind you that
Oh
when
my
we're doing these
gosh.
limits, we're assuming that theta is in radians.
No,
If it's not in
because
radians, we won't get this nice limit of 1 here. So that's our approximation, and we can check it on the calculator, and I actually get an exact value of this number up to 10 decimal
Oh,
places.
snap,
So
bad
as you can see,
sneeze.
this is a really good approximation. We can use this same limit fact again in the next example to calculate this complicated limit as x goes to 0, the limit of tan of 7x over sine of 4x. So when I see tangents and sines in an expression, I'm always tempted to rewrite things in terms of sine and cosine. So I'm going to do that first. I'm going to rewrite tangent as sine over cosine, That's still divided by sine of 4x. And now I'm going to flip and multiply.
I'm missing
to
out
get
my
sine of
freaking
7x
calculus
cosine of 7x
tutorial over
times
this.
1 over sine of 4x. Now, intuitively, if x is near 0, and therefore 7x and 4x are also near 0, then sine of 7x is approximately equal to 7x, and sine of 4x is approximately equal to 4x. So intuitively, this limit should be
Cashew
pretty much
box.
the same thing as the limit as x goes to 0 of 7x over 4. I'm going to rewrite this limit by multiplying by
Wiggle
7x over 7x,
cause.
and by multiplying by 4x over 4x. That hasn't changed. The 7x still can note it is the reciprocal of 1. And as theta goes to 0 of sine theta over theta is equal to 1. And the limit as theta goes to 0 of
ratio.
cosine theta minus 1 over theta is equal to 0. There's a nice proof of these facts in a later video for this section. When you compose two functions, you apply the first function, and then you apply the second function to the output of the first function. For example, the first function might compute population size from time in years. So its input would be time in years since a certain date, and its output would be number of people in the population. The second function, g, might compute healthcare costs
Is that
as a function of
population?
size. So it will take population size as input, and its output will be healthcare costs. If you put these functions together, that is, compose them, then you'll go all the way from time in years to healthcare costs. This is your composition, g composed with f. The composition of two functions, written g with a little circle, f of x, is defined as follows. G composed with f of x is g evaluated on f of x. We can think of it schematically in this diagram. F acts on a number x and produces a number f of x. Then g takes that output f of x and produces a new number, g of f of x. Our composition of functions, g composed with f, is the function that goes all the way from x to g of f of x. Let's work out some examples where our functions are defined by tables of values. If we want to find g composed with f of 4, by definition, this means g of f of 4. To evaluate this expression, we always work from the inside out. So we start with the x value of 4, and we find f of 4 using the table of values for f of x. When x equals 4, f of x is 7.
I'll show you an
So we replace
update,
f of 4
so
with the number 7. Now we need to evaluate g of 7.
here's my
7 becomes our
notes.
new x value in our table of values for g. The
Yeah,
x value of 7 corresponds
here's
to
my
the
other
g of x
notes.
value of 10, so g of 7 is equal to 10. We found that g composed with f of 4 is
Alright.
equal to 10. If
Well,
we
we've
want
got
to
like
find f composed with g of 4,
G7
well, we can rewrite that as f
equals
of
square
g of 4,
root.
and again, work from the inside out. Now we're trying to find g of 4. So 4 is our x value, and we use our table of values for g to see that g of 4 is 1. So we replace g of 4 by 1, and now we need to evaluate f of 1.
It's
In our table
important.
for f values, f of 1 is 8. Notice that when we
Nice.
computed g of f
I
of 4,
believe in
we
you.
computed f of g of 4. And in general, g composed
Bro,
with f is
right
the same thing as g composed with 4.
you know my head
Let's take a
sometimes.
moment to compute the next examples.
I'm
Replace
trying to
f
learn
of 2 by
freaking
2
calculus.
of f of
Yo,
2.
this is my
When
notes,
we
by the
use
way.
we know that f of 2
Chat, what do
is
you think
3,
of my notes?
and f
You
of
got my
2
other
is
notes
6.
here?
If we want to find f composed
What do you
with
think of my
6,
notes,
we
chat?
use
Let me
f
know.
of g of 6 using the
Chat,
table for g,
chat,
g
what do you
of
think of
6
my
is 8.
notes?
But f
Tell me,
of
chat.
8 is not on
Tell
the
me
table as a value
Sigma.
for the f function, and so there is no f of 8. This does not exist.
Sigma
We
W,
can say that 6 is
W,
not in the domain
W6B.
for f composed with
What do you
g.
think of my
Even
notes?
though it was in the domain of g, we couldn't follow all the way through and get a value for f composed with g of 6.
Sigma.
Next, let's turn our attention to the composition of functions that are
W
given by
man,
equations.
we got a Sigma
P
in
of
the
x is squared
chat.
plus x, and q of x is negative 2x. We want to find q composed with p of 1.
Also, while I'm here, yeah, bro, watch this.
Comment section decides what I go for actual week. I'm in high school, by the way. I'm not afraid of your comments. Tell me what is it. The comment section decides.
Yeah, this is what we have, chat. We got dehydrated water on this guy. This guy's like gnarly, guys. Hell nah, chat, what the hell? Yeah, I look like Lloyd. I got the Lloyd cut.
I'm not afraid of your comments. Tell me what is it.
Minecraft and Portal.
Alright, back to calculus.
As usual, I can rewrite this as q of, so this where it's formula for the to compute q composed with p of 1.
Back to learning calculus.
I could just use this expression now. Negative 2 times 1 squared minus 2, and I get negative 4, just like I did before.
With that headache.
Let's try another one. Let's try p composed with q of x. First, I rewrite this, p of q of x. Working from the inside out, I can replace q of x with negative 2x. So I need to compute p of negative 2x. Here's my formula for p. to compute p of this expression, I need to plug in this expression everywhere I see an x in the formula for p. So that means negative 2x squared plus negative 2x. Again, being careful to use parentheses to make sure I plug in the entire expression in for x. Let me simplify. This is 4x squared minus 2x. Notice that I got different expressions for q of p of x and for p of q of x. Once again, we see that q composed with p is not necessarily equal to p composed with q. Please pause the video and try this last example yourself. Rewriting and working from the inside out, we can replace p of x with its expression x squared plus x, and then we need to evaluate p on x squared plus x. That means we plug in x squared plus x everywhere we see an x in this formula. So that's x squared plus x quantity squared plus x squared plus x. Once again, I can simplify by distributing out. That gives me x to the fourth plus 2x cubed plus x squared plus x, or x to the fourth plus 2x cubed plus 2x squared plus x. In this last set of examples, we're asked to go backwards. We're given a formula for a function of h of x, but we're supposed to rewrite h of x as a composition of two functions, f and g. Let's think for a minute which of these two functions gets applied first. F composed with g of x, let's see, that means f of g of x. And since we evaluate these expressions from the inside out, we must be applying g first, and then f. In order to figure out what f and g could be, I need to draw a box around something inside my expression for h. So I'm going to draw a box around x squared plus 7. Then whatever's inside the box, that'll be my function g of x, the first function that gets applied. Whatever happens to the box, in this case taking the square root sign, that becomes my outside function, my second function, f. So here, we're going to say g of x is equal to x squared plus 7, and f of x is equal to the square root of x. Let's just check and make sure that this works. So I need to check that when I take the composition, f composed with g, I need to get the same thing as my original h. So let's see, if I do f composed with g of x, well, by definition, that's f of g of x. Working from the inside out, I can replace g of x with its formula, x squared plus 7. So I need to evaluate f of x squared plus 7. That means I plug in x squared plus 7 into the formula for f, so that becomes the square root of x squared plus 7. Ta-da! It works because it matches my original equation. So we found the correct answer, the correct way of breaking h down as a composition of two functions. But I do want to point out that's not the only correct answer. I'll write down my formula for h of x again, and this time I'll put the box in a different place. I'll just box the x squared. If I did that, then my inside function, my first function, g of x, would be x squared. And my second function is what happens to the box. So my f of x is what happens to the box, and the box gets added 7 to it and taken the square root. So in other words, f of x is going to be the square root of x plus 7.
Yeah, I should
Again, I
chuck
can
this
check if this
out
works.
here.
If I do f composed with g of x, that's f of
Get
g
all
of
my
x.
pop
So now
up.
g of x is x squared, so I'm taking f of x squared. When I plug in x squared for x, I do in fact get the square root of x squared plus 7. So this is the alternative correct solution. In this video, we learned to evaluate the composition of functions by rewriting it and working from the inside out. We also learned to break apart a complicated function into a composition of two functions by boxing one piece of the function and letting the first function applied in the composition, let that be the inside of the box, and the second function applied in the composition be whatever happens to the box. This video is about solving rational equations. A rational equation, like this one, is an equation that has rational expressions in it. In other words, an equation that has some variables in the
Yeah,
denominator.
wait, I could add
There are
way
several different
more
approaches for solving a rational
stuff.
equation, but they all start by finding the least common denominator. In this example, the denominators are x plus 3 and x. We can think of 1 as just having a denominator of 1. Since the denominators don't have any factors in common, I can find the least common denominator just by multiplying them together. My next step is going to be clearing the denominator. By this, I mean that I multiply both sides of my equation by this least common denominator, x plus 3 times x. So I multiply it on the left side of the equation, and I multiply by the same thing on the right side of the equation.
Oh, crap,
Since I do the
crap,
same thing on both sides of
crap.
the equation, I can change the value of the equation. Multiplying the least common denominator on both sides of the equation is equivalent to multiplying it by all three terms in the equation. I can see this when I multiply out. I'll rewrite the left side the same as before, pretty much, and then I'll distribute the right side to get x plus 3 times x times 1 plus x plus 3 times x times 1 over x. So I've actually multiplied the least common denominator by all three terms of my equation. Now I can have a blast canceling things. The x plus 3 cancels with the x plus 3 in the denominator. Here nothing cancels out because there's no denominator, and here the x in the numerator cancels with the x in the denominator. So I can rewrite my expression as x squared equals x plus 3 times x times 1 plus x plus 3.
We gotta get the
Now I can
OG
simplify.
pop up.
So I'll leave the x squared alone. On this side, I'll distribute out x squared plus 3x plus x plus 3. Hey, look, the x squareds cancel on both sides. And so I get 0 equals 4x plus 3. So 4x is negative 3, and x is negative 3/4. Finally, I'm going to plug in my
Nice, people, nice.
important
Pose.
for a rational equation, because occasionally for rational equations, you'll get what's called extraneous solutions, solutions that don't actually work in your original equation because they make the denominator 0. Now, in this example, I don't think we're going to get any extraneous equations because negative 3/4 is not going to make any of these denominators 0. So it should work out fine when I plug in. If I plug in, I get this. I can simplify the denominator here, negative 3/4 plus 3. 3 is 12/4, that becomes 9/4. And this is 1. I'll flip and multiply to get minus 4/3. So
Whoa,
here I
whoa,
can
whoa,
simplify
whoa,
complex fraction. It ends up
whoa.
being negative 3/9.
Alright,
1 minus
that's
4/3
enough.
is negative 1/3. So that all seems to check out. And so my final answer is x equals negative 3/4. This next example looks a little trickier, and it is, but the same approach will work. First, I'll find the least common denominator. So here, my denominators are c minus 5, c plus 1, and c squared minus 4c minus 5. I'm going to factor that as c minus 5 times c plus 1. Now, my least common denominator needs to have just enough factors that each of these denominators divide into it. So I need the factor c minus 5, I need the factor c plus 1, and now I've already got all the factors I need for this denominator. So here is my least common denominator. Next step is to clear the denominators. So I do this by multiplying both sides of the equation by my least common denominator. In fact, I can just multiply each of the three terms by this least common denominator. I went ahead and wrote my third denominator in factored form to make it easier to see what cancels. Now, canceling time.
Oh my
That dies.
god.
This dies. And both of those factors die. Canceling out the denominator is the whole point of multiplying by the least common denominator. You're multiplying by something that's big enough to kill every single denominator, so you don't have to deal with denominators anymore. Now I'm going to simplify by multiplying out. So I get, let's see, c plus 1 times 4c, that's 4c squared plus 4c. Now I get minus, just c minus 5, and then here I get 3c squared plus 3. I can rewrite the minus quantity c minus 5 as minus c plus 5. And now I can subtract the 3c squared from both sides to get just a c squared over here.
Far away log.
And
We're like
4c
5
minus
hours
c, that
in.
becomes a 3c. Didn't draw any parts of the graph over here with negative x values, and I didn't put any negative x values on my chart. That omission is no accident, because if you try to take the log base 2 or base anything of a negative number, like say negative 4 or something, there's no answer. This doesn't exist because there's no...
I tried everything, coffee, Pomodoro, and binaural beats, but nothing stuck until I tried this.
no power that you can raise 2 to get a negative number. So there are no points on the graph for negative x values. And similarly, there are no points on the graph where x is 0, because you can't take log base 2 of 0. There's no power you can raise 2 to get 0. I want to observe some key features of this graph. First of all, the domain is x values greater than 0. In interval notation, I can write that as a round bracket, because I don't want to include 0, to infinity. The range is going to be the y values. Well, they go all the way down into the far reach of the negative numbers, and the graph gradually increases, y values getting bigger and bigger, so the range is actually all real numbers. Or in interval notation, negative infinity to infinity. Finally, I want to point out that this graph has a vertical asymptote at the y-axis, that is, at the line x equals 0. I'll draw that on my graph with a dotted line. A vertical asymptote is a line that our function's graph gets closer and closer to. So this is the graph of y equals log base 2 of x. But if I wanted to graph, say, y equals log base 10 of x, it would look very similar. It would still have a domain of x values greater than 0, a range of all real numbers, and a vertical asymptote of the y-axis. It would still go through the point 1, 0, but it would go through the point 10, 1 instead, because log base 10 of 10 is 1. It would look pretty much the same, just a lot flatter over here. But even though it doesn't look like it with the way I've drawn it, it still gradually goes up towards infinity. In fact, the graph of y equals log base any a of x for a bigger than 1 looks pretty much the same and has these same 3 properties. Now that we know what the basic log graph looks like, we can plot at least rough graphs of other log functions without plotting points. Here we have the graph of natural log of x plus 5. And again, I'm just going to draw a rough graph. If I did want to do a more accurate graph, I probably would want to plot some points. But I know that roughly a log graph, if it was just like y equals ln of x, that would look something like this, and it would go through the point 1, 0, with a vertical asymptote along the y-axis. Now if I want to graph ln of x plus 5, that just shifts our graph up by 5 units. It'll still have the same vertical asymptote, since a vertical line shifted up by 5 units is still a vertical line, but instead of going through 1, 0, it'll go through the point 1, 5. So I'll draw a rough sketch here. Let's compare our starting function, y equals ln x, and the transformed version, y equals ln x plus 5, in terms of the domain, the range, and the vertical asymptote. Our original function, y equals ln x, had a domain of 0 to infinity. Since adding 5 on the outside affects the y values, and the domain is the x values, this transformation doesn't change the domain. So the domain is still from 0 to infinity. Now the range of our original y equals ln x was from negative infinity to infinity. Shifting up by 5 does affect the y values, and the range is talking about the y values, but since the original range was all real numbers, if you add 5 to a set of all real numbers, you still get the set of all real numbers. So in this case, the range doesn't change either. And finally, we already saw that the original vertical asymptote of the y-axis, x equals 0, when we shift that up by 5 units, it's still the vertical line, x equals 0. In this next example, we're starting with a log base 10 function, and since the plus 2 is on the inside, that means we shift that graph left by 2. So I'll draw our basic log function. Here's our basic log function, so I'll think of that as y equals log of x, going through the point 1, 0. Here's its vertical asymptote. Now I need to shift everything left by 2. So my vertical asymptote shifts left, and now it's at the line x equals negative 2 instead of at x equals 0. And my graph, well, let's see, my point, 1, 0, gets shifted to, let's see, negative 1, 0, since I'm subtracting 2 from the x's. And here's a rough sketch of the resulting graph. Let's compare the features of the two graphs drawn here. We're talking about domains. The original had a domain of from 0 to infinity. But now I've shifted that left, so I subtracted 2 from all my x values, and here's my new domain, which I can also verify just by looking at the picture. My range was originally from negative infinity to infinity. Well, shifting left only affects the x value, so it doesn't even affect the range, so my range is still negative infinity to infinity. My vertical asymptote was originally at x equals 0, and since I subtract 2 from all my x values, that shifts it to x equals negative 2. In this last problem, I'm not going to worry about drawing this graph. I'll just use algebra to compute its domain. So let's think about what's the issue when you're taking the logs of things. Well, you can't take the log of a negative number or 0, so whatever's inside the argument of a log function, whatever's being fed into log, had better be greater than 0. So I'll write that down. We need 2 minus 3x to be greater than 0. Now it's a matter of solving an inequality. 2 has got to be greater than 3x, so 2/3 is greater than x. In other words, x has to be less than 2/3, so our domain is all the x values from negative infinity to 2/3, not including 2/3. It's a good idea to memorize the basic shape of the graph of a log function. It looks something like this, 1, 0, and has a vertical asymptote on the y-axis. Also, if you remember that you can't take the log of a negative number or 0, then that helps you quickly compute domains for log functions. Whatever's inside the log function, you set that greater than 0 and solve. This video is about combining logs and exponents. Please pause the video and hit the log button. Plus log of z. When I put things together, I have to be careful because here I'm subtracting the entire log expression. So I need to subtract both terms of this sum. I'll make sure I do that by putting them in parentheses. Now I can simplify a little bit by distributing the negative sign. And here's my final answer. In my next expression, I have the log of a product, so I can rewrite that as the sum of two logs. I can also use my power rule to bring down the exponent t and multiply it in the front. That gives me the final expression, log of 5 plus t times log of 2. All I see about this problem is to rewrite this expression as t times log of 5 times 2. In fact, those two expressions are not equal. Because the t only applies to the 2, not to the whole 5 times 2, we can't just bring it down in front using the power rule. After all, the power rule only applies to a single expression raised to an exponent, and not to a product like this. In these next examples, we're going to go the other direction. Here we're given sums and differences of logs, and we want to wrap them up into a single log expression. If I look at the first two pieces, that's a difference of logs. So I know I can rewrite it as the log of a quotient. Now I have the sum of two logs, so I can rewrite that as the log of a product. I'll clean that up a little bit and rewrite it as log base 5 of a times c over b. In my second example, I can rewrite the sum of my logs as the log of a product. Now I would like to rewrite this difference of logs as the log of a quotient, but I can't do it yet because of that factor of 2 multiplied in front. But I can use the power rule backwards to put that 2 back up in the exponent. So I'll do that first. So I will copy down the ln of x plus 1 times x minus 1 and rewrite the second term as ln of x squared minus 1 squared. Now I have a straightforward difference of two logs, which I can rewrite as the log of a quotient. I can actually simplify this some more. Since x plus 1 times x minus 1 is the same thing as x squared minus 1, I can cancel factors to get ln of 1 over x squared minus 1. In this video, we saw 4 rules for logs that are related to exponent rules. First, we saw that the log with any base of 1 is equal to 0. Second, we saw the product rule, the log of a product is equal to the sum of the logs. We saw the quotient rule, the log of a quotient is the difference of the logs. And we saw the power rule. When you take a log of an expression with an exponent in it, you can bring down the exponent and multiply it. It's worth noticing that there's no log rule that helps you split up the log of a sum. In particular, the log of a sum is not equal to the sum of the logs. If you think about logs and exponent rules going together, this kind of makes sense, because there's also no rule for rewriting the sum of two exponential expressions. Log rules will be super handy as we start to solve equations using logs. The chain rule is a really useful method for finding the derivative of the composition of two functions. Let's start with a brief review of composition.
Let's show these off.
F composed with g means that we apply f to the output of g. As a diagram, this means we start with x and apply g first, then we apply f to the output to get our final result. I'm going to call g the inner function,
Yo,
and f
probably
the
there
outer
was
function,
lotion here.
because g looks like it's on the inside of f in the standard notation. We can write h of x, which is the square root of sine of x, as the composition of two functions, by letting sine of x be the inner function, and the square root function be the outer function.
Yo,
That f of u
what?
equals the square root of u. I like to do this sort of dissection of functions by drawing a box around part of the function. Whatever's inside the box becomes my inner function,
Like it.
and whatever we do to the box becomes our outer function, in this case, taking the square root. This allows us to write h of x as the composition f of g of x, where f and g are the outer and inner functions defined here. Please take a moment to write the next two functions as compositions of functions before you go on. A natural way to write k of x as a composition is to let our inner function be tan of x plus secant of x. The outer function describes what happens to that box.
Don't know what that was. They
It gets
lagged
cubed
out.
and multiplied by 5.
Oh, that was
There's
laggy
several ways to write the
internet.
next
Don't
example
know
as a
what
composition
that
of functions.
was. They
For
lagged
example,
out.
we could take x squared as our inner function, and then our outer function
Low.
takes e to the sine of that inner function. Alternatively, we could take the inner function to be sine of x squared, and then the outer function has to be e to the power. It's also possible to write our function r of x as a composition of 3 functions. An inner function of x squared, a middle function of sine, and an outer function of e to the power, which I'll write as h of b equals e to the b. When calculating the derivatives of complicated functions, it's really important to recognize them as compositions of simple functions. That way we can build up the derivative in terms of simpler derivatives. And that's the idea behind the chain rule. The chain rule tells us if we have two differentiable functions, then the derivative of the composition, f composed with the derivative of the outer function, evaluated on the inner function, times the derivative of the inner function. Sometimes the chain rule is written instead in Leibniz notation, that is the dy dx notation. To
No.
see how this works, let's let u equal g of x, and let's let y equal...
Stuck on what uni course is right for you? Fair enough. There are so many options to choose from. If only there was an easy quiz to help you narrow it down. See where I'm going with this, don't you? To make life easier, take our quick Help Me Choose quiz to compare courses from leading Australian universities.
We're going to the baddest days.
Head to open.edu.au to give it a go and see what pops up for you. Open.edu.au to give it a go and see what pops
equal
up.
f of u. In other words, y is f of g of x. Now, du dx is just another way of writing g prime of x, and dy du is another way of writing f prime of u, or in other words, f prime of g of x. Finally,
Anyway,
we
chat.
write dy dx.
So I've built up like these like
taking the
comments.
derivative of f
Oh,
composed
the
with g.
green.
So that's f composed with g prime of x. Using this key, I can rewrite the expression above as
Yeah,
dy dx
I'm doing up these
equals
like comments.
dy du times
wall
du dx.
like
These are the two alternative ways of writing the
that.
chain rule. Let's use the chain rule to take the derivative of the square root of sine x. Actually, I'm going to rewrite this as h of x equals sine x to the 1/2 power to make it easier to take derivatives. As a
So we have
composition,
this one.
we have the
It's
inner
like
function as sine x and the outer function as the 1/2 power. So the chain rule tells us that to take h prime of x,
yeah,
we
you
need to
can
take
see
the
it
derivative of
there.
the outer function, evaluate it
It's
on the
like
inner
all
function,
wavy with
and
the
then multiply that by the
printer.
derivative of the inner function.
The second one's
We know
this
that the
one,
derivative of the inner function, sine x, is
which
just cosine x,
is
and the derivative of the outer function is
what?
1/2 times u to the negative 1/2. So h prime of x is then 1/2 times u to the negative 1/2, but that's evaluated on the inner function, sine of x, and then we multiply that by cosine of x. Again, that's the derivative of the outer function evaluated on the inner function times the derivative of the inner function. And we found the derivative using the chain rule. For the next example, our inner function was tan x plus secant x, and our outer function, f of u, was 5u cubed.
Yeah, the skelly bird.
So k prime of x is 15 times u squared, but that's evaluated on the inner function, tan x plus secant x. Then we're going to
Casually
multiply that
eating the
by the
verse
derivative
verse.
of the inner function, tan x plus secant x. So we get the 15 tan x plus secant x squared times the derivative of tan x, which is secant squared x, plus the derivative of secant x, which is secant x tan x. And that's our chain rule derivative. In this last example, we're thinking of the outermost function as being e to the power, and its inner function is sine of x squared. But
Oh
sine of x
snap,
squared
we're
is
learning about E.
sine and an inner function of x squared. So to find r prime of x, we first have to take the derivative of the outermost function. Well, the derivative of e to the power is just e to the power, and now we evaluate that on its inner function, sine of x squared. But now by the chain rule, we have to multiply that by the derivative of the inner function, sine of x squared. The outer function is take the power of a power, I multiply the exponent. And remember, e to the ln 5 is just a fancy way of writing 5. So I've got 5 to the x times ln 5 as the derivative with respect to x of 5 to the x. This same argument works not just for a base 5 exponential function, but for any base exponential function. So if I take the respect to x of a to the x for any number a, I'm going to get
Oh yeah,
a
and
to the
then
x times ln a.
the
And
next
we're
one
going
is
to apply the
this.
same rule on our old favorite, e to the x. So our base here is e. That means I should get e to the x times ln e. Wait a sec. ln e, that's log base e of e. That's asking what power do I raise e to get e? Well, the answer there is 1. And so the derivative with respect to x of e to the
Like
x
3
is
others
the
that
new rule we
are
have,
finished
e to
from
the x,
there.
which agrees with our old rule. I want to draw your attention to the difference between two expressions. In the first expression, d dx of a to the x, the variable that we're taking the derivative with respect to is in the exponent. So for this exponential function, we use the derivative rule that we just found, d dx of a to the x is a to the x times ln a. On the other hand, if we take the respect to x of x to the a, where the variable x that we're taking the derivative with respect to is in the base, then we don't need this exponential rule. In fact, it doesn't even apply. All that we have here is the power rule, right? d dx of x cubed would be 3x squared, d dx of x to the 7th would be 7x to the 6th, and in general, d dx of x to the a is just a times x to the a minus 1 by the power rule. So it's important to pay attention to where the variable is when you're taking a derivative. In this video, we found that the derivative with respect to x of 5 to the x is given by ln 5 times 5 to the x. And in general, the derivative of respect to x of a to the x is going to be ln a times a to the x. This gives us a general formula for the derivative of exponential functions. The main goal of this video is to figure out the derivatives of logarithmic functions, functions like y equals ln x, or y equals log base ax for any positive base a. I want to find the derivative of log base a of x. In other words, I want to find the derivative of y, where y is log base a of x. By the definition of logarithms, log base a of x equals y means that a to the y power is equal to x. And that's useful because now I can take the derivative of both sides and use implicit differentiation. Recall that the derivative of a to the power is ln a times a to the power, but since y we're thinking of as a function of x, I have to multiply that by dy dx by the chain rule. The right-hand side here is just 1. Solving for dy dx, I get 1 over ln a times a to the y. But since a to the y is equal to x, I can rewrite that as dy dx equals 1 over ln a times x. So the derivative of log base a of x for any base a is 1 over ln of a times x. And in particular, the derivative of natural log of x is 1 over ln of e times x. But since ln of e is just 1, that's saying that the derivative of ln x is 1 over x. This is a very handy fact. And this more general derivative is also worth memorizing. While we're talking about the derivative of the natural log of x, let's look at the derivative of the natural log of the absolute value of x. The function y equals ln of absolute value of x is of course closely related to the function y equals ln of x. The difference being that the domain for ln x is just x values greater than 0, whereas the domain of ln of absolute value of x is all x's not equal to 0. The graphs are also related. When you look at the graph of y equals ln absolute value of x, it looks like you're seeing double. Since the absolute value of x is equal to x when x is greater than or equal to 0 and negative x when x is less than 0, ln of the absolute value of x is going to be equal to ln x when x is greater than or equal to 0 and ln of negative x when x is less than 0. If I consider the derivative of ln of absolute value of x, I can think of taking the derivative of each piece separately. We just saw that the derivative of ln x is 1 over x, so the derivative of ln of minus x is going to be 1 over minus x times the derivative of minus x, which is minus 1, by the chain rule. Notice that this second expression simplifies to 1 over x. So the derivative of ln of absolute value of x is equal to 1 over x, whether x is positive or negative. This formula will come in handy later when we start doing integrals. In this video, we found that the derivative of ln x is equal to 1 over x, kind of a nice derivative. And more generally, the derivative of log base a of x is 1 over ln a times x. We've seen previously that the derivative of x to a constant a is equal to a times x to the a minus 1. This is the power rule. We've also seen that the derivative of a positive number a raised to the x power is equal to ln a times a to the x. So we know how to take the derivative when the variable x is in the base or when it's in the exponent, but what if the variable is in both the base and the exponent? How do we take the derivative of x to the x? To differentiate functions like this, we'll need to use the technique of logarithmic differentiation. To find the derivative of x to the x, I'm going to set y equal to x to the x. Now we want to find dy dx. Since we don't know how to compute dy dx directly, let's take the natural log of both sides. Taking the log is often a handy trick when you have a variable in the exponent that you don't know how to deal with, because the properties of logs allow us to bring that exponent down and multiply it. Now we have y implicitly defined in terms of x, so let's use implicit differentiation. We'll take the derivative of both sides with respect to x. And now we should have no trouble taking the derivatives because we've gotten rid of the awkward exponential expression. So the derivative on the left of ln y is 1 over y times dy dx, and the derivative on the right using the product rule is x times 1 over x plus 1 times ln x. This simplifies to 1 over y dy dx equals 1 plus ln x. So dy dx is going to equal y times 1 plus ln x, and replacing y with x to the x, I have dy dx is x to the x times 1 plus ln x. This technique of taking the log of both sides, differentiating, and solving for dy dx is known as logarithmic differentiation, and it's enormously useful whenever you have variables in both the base and the exponent. Here's another example where our variable is in both the base and the exponent. So as before, I'm going to set y equal to the expression that I want to differentiate and compute dy dx. First, I'll take the log of both sides, use my log rules to bring my exponent down and multiply it, and take the derivative of both sides with respect to x. On the left, I get 1 over y dy dx, and on the right, I get 1 over x times the derivative of ln tangent x, which is 1 over tangent x times the derivative of tangent x, or secant squared x. Continuing with the product rule, I need to take the derivative of 1 over x. That's going to be the derivative of x to the minus 1, which is minus 1 times x to the minus 2 times ln tangent of x. Simplifying the right-hand side, I get 1 over x times 1 over sine x over cosine x times 1 over cosine squared x minus ln tan x over x squared. Rewriting, I can flip and multiply to get 1 over x times cosine x over sine x times 1 over cosine squared x minus the second term. Canceling one copy of cosine and rewriting in terms of cosecant and secant, I get this expression. I still have to solve for dy dx, so multiplying both sides by y, I get the following. And since y was equal to tan x to the 1 over x, I can rewrite everything in terms of x. The technique of logarithmic differentiation is most useful when taking the derivative of an expression that has a variable in both the base and the exponent, like in this example. But sometimes it's also handy just as a way to take the derivative of a complicated product and quotient, like in this example. Now we could take the derivative here just by using the quotient rule and the product rule, but it's a little easier to take the log of both sides. And the reason is that when we take the log of a product, we get a sum, and the log of a quotient is a difference, and sums and quotients are a lot easier to deal with. So in this example, the log of y is equal to ln of x plus ln of cosine of x minus ln of x squared plus x to the 5th power. I can even bring that 5th power down, because that's another one of my log rules. Now it's much more straightforward to take the log of both sides. On the left, I have 1 over y dy dx, as usual, and on the right, the derivative of ln x is 1 over x, the derivative of ln cosine x is 1 over cosine of x times negative sine of x, and the derivative of ln x squared plus x is 1 over x squared plus x times 2x plus 1. I'll solve for dy dx and get y times 1 over x minus sine x over cosine x, that's the same as tangent x, minus 5 times 2x plus 1 over x squared plus x. Now I can just rewrite y in terms of x and I'll be done. Again, I didn't have to use logarithmic differentiation to find this derivative. I could have just used the product rule and the quotient rule, but logarithmic differentiation made it computationally much easier. In this video, we learned how to take the derivative of expressions that have a variable both in the base and in the exponent. And the idea was, first, to set y equal to the expression we want to derive, next, to take the natural log of both sides, next, to derive both sides, and finally, to solve for dy dx. This process is called logarithmic differentiation. The inverse of a function undoes what the function does. So the inverse of tying your shoes would be to untie them. And the inverse of the function that adds 2 to a number would be the function that subtracts 2 from a number. This video introduces inverses and their properties. Suppose f of x is the function defined by this chart. In other words, f of 2 is 3, f of 3 is 5, f of 4 is 6, and f of 5 is 1. The inverse function for f, written f superscript negative 1 x, undoes what f does. Since f takes 2 to 3, f inverse takes 3 back to 2. So we write this, f superscript negative 1 of 3 is 2. Similarly, since f takes 3 to 5, f inverse takes 5 to 3. And since f takes 4 to 6, f inverse of 6 is 4. And since f takes 5 to 1, f inverse of 1 is 5. I'll use these numbers to fill in the chart. Notice that the chart of values when y equals f of x and the chart of values when y equals f inverse of x are closely related. They share the same numbers, but the x values for f of x correspond to the y values for f inverse of x, and the y values for f of x correspond to the x values for f inverse of x. That leads us to the first key fact. Inverse functions reverse the roles of y and x. I'm going to plot points for y equals f of x in blue.
Real, bro.
Next, I'll plot the points for y equals f inverse of x in red. Pause the video for a moment and see what kind of symmetry you observe in this graph. How are the blue points related to the red points? You might have noticed that the blue points and the red points are mirror images. over the mirror line y equals x. So our second key fact is that the graph of y equals f inverse of x can be obtained from the graph of y equals f of x by reflecting over the line y equals x. This makes sense because inverses reverse the roles of y and x. In the same example, let's compute f inverse of f of 2. This open circle means composition. In other words, we're computing f inverse of f of 2. We compute this from the inside out. So that's f inverse of 3, since f of 2 is 3, and f inverse of 3 we see as 2. Similarly, we can compute f of f inverse of 3, and that means we take f of f inverse of 3. Since f inverse of 3 is 2, that's the same thing as computing f of 2, which is 3. Please pause the video for a moment and compute these other compositions. You should have found that in every case, if you take f inverse of f of a number, you get back to the very same number you started with. And similarly, if you take f of f inverse of any number, you get back to the same number you started with. So in general, f inverse of f of x is equal to x, and f of f inverse of x is also equal to x. This is the mathematical way of saying that f and f inverse undo each other. Let's look at a different example. Suppose that f of x is x cubed. Pause the video for a moment and guess what the inverse of f should be. Remember, f inverse undoes the work that f does. You might have guessed that f inverse of x is going to be the cube root function. And we can check that this is true by looking at f of f
For real hobbies!
cube root of function, which means the cube root function cubed, which gets us back to x. Similarly, if we compute f inverse of f of x, that's the cube root of x cubed, and we get back to x again. So the cube root function really is the inverse of the cubing function. When we compose the two functions, we get back to the number that we started with.
Probably like write this down.
It'd be nice to have
You
a more
know,
systematic way of finding inverses of functions.
big test on algebra
One
type
is the
crap.
fact that inverses reverse the roles of y and x. So if we want to find the inverse of the function f of x equals 5 minus x over 3x, we can write it as
Head
y
start.
equals 5 minus x over 3x, reverse the roles of y and x to get x equals 5 minus y over 3y, and then solve for y. To solve for y, let's multiply both sides by 3y, bring all terms with y's in them to the left side, and all terms without y's in them to the right side, factor out the y, and divide to isolate y. This gives us f inverse of x as 5 over 3x plus 1. Notice that our original function, f,
We
and our
got
inverse
like
function, f
f,
are both rational functions, but they're not the reciprocals of each other. And in general,
x,
f inverse of x is not usually equal to 1 over f of x. This can be confusing because when we write
we skip
and the
most of
range of
this.
f is the domain of f inverse. These properties of inverse functions
Bacon.
will be important when we study exponential functions and their inverses, logarithmic functions. This video defines the standard inverse trig functions: sine
I
inverse,
got the same
cosine
special
inverse,
case
and tan
symbol.
inverse.
Equal
Please focus first on the thick black line. This is
domain.
the graph of y equals sine x. The graph of the inverse of a function can be found by flipping the graph of the original function over the line y equals x. I've drawn the flip graph with this blue dotted line. But you'll notice that the blue dotted line is not the graph of a function because it violates the vertical line test. So in order to get a function that's the inverse of y equals sine x, we need to restrict the domain of sine x. We'll restrict it to this piece that's drawn with a thick black line. If I invert that piece by flipping it over the line y equals x, I get the piece drawn with a red dotted line here. And that piece does satisfy the vertical line test, so it is in fact a function. Although regular sine x has domain from negative infinity to infinity, our restricted sine x has domain from negative pi over 2 to pi over 2. Its range is still from negative 1 to 1, just like the regular sine x, because I've taken the biggest possible piece of the graph whose flipped version is still a function. The inverse sine function is often written as arc sine of x. And since inverting the function reverses the roles of y and x, it reverses the domain and the range. So arc sine of x, the inverse function, has domain from negative 1 to 1 and range from negative pi over 2 to pi over 2, which seems plausible from the graph. Now an inverse function undoes the work of a function. So if the function sine takes angles theta to numbers x, then the inverse sine is equal to arc sine x, means that x is equal to
pi over 2.
Angles y whose sine is x, right? They all differ by multiples of 2 pi. We specify also that y is between negative pi over 2 and pi over 2. That was the whole point of doing this domain restriction. Negative 1 does not equal 1 over sine of x. 1 over sine of x, the reciprocal function, is another word for cosecant of x. But sine to the negative 1 of x is another word for arc sine of x, the inverse sine function, which is not the same thing as the reciprocal function. Let's go through the same process to build an inverse cosine function. We start with the graph of cosine of x. We flip it over the line y equals x to get the blue dotted line, but the blue dotted line is not a function, so we go back and restrict the domain for our original cosine of x to just be between 0 and pi. The resulting red graph now satisfies the vertical line test, so it's a proper inverse function. Our restricted cosine has domain from 0 to pi and range from negative 1 to 1, and so on takes us from x, and it's not equal to 1 over tan of x, which is called cotangent of x. And that's all for this video on the 3 basic inverse trig functions. Sine inverse x, also known
Just now we should write that down. A1 and x 05.
as arc sine of x, cosine inverse x, also known as arc cosine x, and tan inverse x, also known as arc tan x. In this video, we'll use implicit differentiation to find the derivatives of the inverse trig functions. First, the inverse sine function. Recall that y equals sine inverse of x means that y is the angle in radians whose sine is x. In other words, we can write x equals sine of y as an almost equivalent statement. I say almost equivalent because there are lots of different y's whose sine is x. Lots of different angles can have the same resulting sine. And for the inverse sine function, we specify that that angle y has to be between pi over 2 and negative pi over 2. That's just the convention. Be careful not to mistake sine inverse of x, which is an inverse function, and 1 over sine x, which is a reciprocal function. These are not the same thing. This negative 1 does not mean reciprocal here, it means inverse function. There is another notation for inverse sine, which is arc sine. So arc sine of x is the same thing as sine inverse of x. We want to find the derivative of sine inverse of x. In other words, the derivative of y with respect to x, where y is sine inverse of x. I'm going to rewrite this equation here as x equals sine y, and then use implicit differentiation. So taking the derivative of both sides with respect to x, I have derivative of x is equal to the derivative of sine y. In other words, 1 is equal to cosine of y times dy dx. Solving for dy dx, I have that dy dx is 1 over with x minus x squared by the Pythagorean theorem. Now I can compute cosine of y just from the triangle. Cosine of y is adjacent over hypotenuse, so that's the square root of 1 minus x squared over 1, or just the square root of 1 minus x squared. I've been implicitly assuming that y is a positive angle between 0 and pi over 2 when I've been drawing this triangle, but you can check that the same formula also works if y is a negative angle. Think of it going down here on the unit circle instead of up here. So now that I have a formula for cosine y in terms of x, I can go back to my derivative and substitute, and I get dy dx is 1 over the square root of 1 minus x squared. In other words, I found a formula for the derivative of inverse sine of x. We can carry out a similar process to find the derivative of inverse cosine. Y equals cosine inverse x means that x is equal to cosine of y, and by convention, y lies between 0 and pi. To find the derivative of arc cosine of x, arc cosine is just an alternative notation for cosine inverse. I can write y equals arc cosine of x, and equivalently, x equals the cosine of y, and then I want to find dy dx using implicit differentiation. Please pause the video and try it for yourself before going on. So starting with the equation x equals cosine y, we're going to take the derivative of both sides with respect to x. The derivative of x is 1, and the derivative of cosine y is negative sine y dy dx. So dy dx is equal to negative 1 over sine y. As before, I can draw and label a right triangle. The angle is y, and now I know that x is cosine of y, so I'm going to put x on the adjacent side and 1 on the hypotenuse, leaving the square root of 1 minus x squared on the opposite side, which means that sine of y, which is opposite over hypotenuse, is equal to the square root of 1 minus x squared. And so dy dx is going to be negative 1 over the square root of 1 minus x squared, and I have my formula for the derivative of arc cosine of x. Inverse tangent can be handled very similarly, and again, you may want to try it for yourself before watching the video. Y equals inverse tangent of x means that x is tangent of y, and the convention is that y is supposed to lie between negative pi over 2 and pi over 2. Proceeding as before, we write y equals arctan of x, and x equals tan of y. Take the derivative of both sides. So we get 1 equals secant squared of y dy dx. Solving for dy dx, we have 1 over secant squared of y, and using our right triangle as before, we can label the angle as y. Since I know that tangent y is x, and tangent is opposite over adjacent, I'm going to label the opposite side x and the adjacent side 1, which gives us a hypotenuse of the square root of 1 plus x squared. Now we know that secant of y is 1 over cosine of y, so that's going to be hypotenuse over adjacent. So that's the square root of 1 plus x squared over 1, and so secant squared of y is just the square of this, which is 1 plus x squared. Now I can substitute into my formula for dy dx, and I get dy dx is 1 over 1 plus x squared, which gives me a nice formula for the derivative of inverse tangent. The other inverse trig functions, cotangent inverse, secant inverse, and cosecant inverse, have derivatives that can be computed similarly. The following table summarizes these results. In some books, you may see absolute value signs around the x for the formulas for inverse secant and inverse cosecant. Of course, when x is positive, this makes no difference. And when x is negative, this discrepancy comes from differences in the convention for the range of y for these inverse trig functions, secant inverse and cosecant inverse. Notice that the derivatives of the inverse trig functions that start with co all have negative signs in front of them and are the negatives of the corresponding inverse trig functions without the co. That makes it easier to remember them. You should memorize these formulas. Let's do one example using the formulas that we just found. Let's compute the derivative of tan inverse of a plus x over a minus x. We'll want to use the formula for the derivative of tan inverse x. Now to compute dy dx for our function, we can use the chain rule. The outside function is tan inverse, whose derivative is 1 over 1 plus the inside function squared. We'll need to multiply that by the derivative of the inside function. I'll just copy over the first.
Iconic Europe. 17 days, just $4,749, including flights with Holiday Max. Experience the very best of 7 countries as you stay in charismatic Rome, cruise Amsterdam canals, sip wine in Tuscany, and embrace radiant Paris. Discover all this and more on our 17-day Iconic Europe Escort.
In this video, I'll work through 2 examples of finding extreme values, that is, maximum values and minimum values of functions. In the first example, we're asked to find the absolute maximum and minimum values for this rational function g of x on the interval from 0 to 4. these maximum and minimum values could occur at critical numbers in the interior of the interval, or they could occur at the endpoints of the interval. So we'll need to check the critical numbers and check the endpoints and compare our values. To find the critical numbers, those are the numbers where g prime of x is equal to 0 or does not exist. So let's take the derivative, g prime of x, using the quotient rule. So we get x squared plus x plus 2 squared on the denominator, and then we have low times d high, the derivative of the numerator is 1, minus high times the derivative of the denominator, that's 2x plus 1. Before we figure out where that 0 or doesn't exist, let's simplify it a little bit. So we can multiply out the...
My gosh.
I'll distribute the negative...
Hold on, let me just reinforce my formula.
I'm just leaving the denominator alone on all these steps. So our simplified numerator is going to be minus x squared plus 2x plus 3. Now that I've simplified the derivative, I can figure out...
Chad, I think I've done it.
Doesn't exist. Let me clear a little space. Now the only way that g prime of x could not exist is if the denominator is 0. But on our interval, where x is between 0 and 4, x squared plus x plus 2 is always greater than or equal to 2. So the denominator
What's that? A little bit more working out. Good cut off.
X squared plus x plus 2
Right, chat. Right, we started with this. Now we have this. Right. Important things.
To find where g prime of x is equal to 0, we just have to check where
I'm pretty sure the answer
negative x squared plus 2x plus 3
is
0.
x factorial.
There by negative 1 and a factor. I get that x equals 3 or x equals minus 1. So these are my critical numbers, but notice that one of these critical numbers...
My gosh, it's like top level stuff.
I don't have to worry about it. All I have to worry about is x equals 3.
Where's my pen?
X equals 3 is one place where my function g could have an absolute maximum or minimum. So let's figure out g's value there by plugging in 3 for x.
Oh my gosh.
2/14 or 1/7. So we've checked the critical numbers. Now let's go ahead and check the endpoints. Those are the x values of 0 and 4, since our interval is from 0 to 4. Plugging in, we get that g of 0 is negative 1/2, and g of 4 is 3/22. I sometimes like to make a table of all these candidate values. The candidate x values are 0, 3, and 4, and the corresponding g of x values...
Chat, this is like top level stuff, you know.
Now to find the absolute maximum and minimum values,
Intense.
all I have to do is figure out which one of these y values is the biggest and which is the smallest. Well, clearly, negative 1/2 is the smallest, so that's the absolute minimum value.
My teachings will go insane.
Now, 1/7 is the same as 3/21, which is going to be bigger than 3/22. So 1/7 is our absolute max value. We can confirm this by looking at a graph of our function g. Remember, we're just interested in the interval from 0 to 4, so we're just interested in this section of the graph. And it does look like the minimum value is here at when x equals 0, minimum value of negative 1/2, like we found. And the maximum value, well, I'm not sure exactly where it is from this graph, but it does look like it's somewhere around 3, and that is a value of something around 1/7. So the graph does confirm what we found as a more precise answer using calculus. For the next example, let's find the absolute extreme values for the function f of x, which is the absolute value of x minus x squared, on the interval from negative 2 to 2. As before, we can find absolute extreme values by checking first the critical numbers, and then also the endpoints of the interval, negative 2 and 2. To find the critical numbers, we need to take the derivative of our function. But because our function involves an absolute value, it's a little tricky to take the derivative. Instead, let's first rewrite f using piecewise notation. Recall that if we're looking at the absolute value of x, when x is bigger than or equal to 0, absolute value of x is just x, so f of x will be x minus x squared. On the other hand, when x is less than 0, the absolute value of x is negative x, so f of x will be negative x minus x squared. Now, to take the derivative, we can take the derivative of each piece. So when x is bigger than 0, I don't want to take the derivative when x equals 0 because there might be funny things happening, a cusp or a corner. So I'm just going to worry about when x is bigger than 0 and when x is less than 0 for now. When x is bigger than 0, I can just use the power rule. I get 1 minus 2x as the derivative. When x is less than 0, I get negative 1 minus 2x. And now to find where I have critical numbers, I need to find where f prime of x is equal to 0 or f prime of x does not exist. Well, f prime of x equals 0, where 1 minus 2x equals 0 for x bigger than 0, and where negative 1 minus 2x is equal to 0 for x less than 0. So that corresponds to x equal 1/2 for x bigger than 0, and x equals negative 1/2 for x less than 0. So those are my first two critical numbers. Notice they do lie within my interval that I'm interested in. But I also have to worry about where f prime of x does not exist, and the candidate x value for that is where x equals 0. One way to convince ourselves that the derivative does not exist when x equals 0 is to look at the fact that the derivative is very close to 1 for x values, very close to 0 from the right side, and very close to negative 1 for x values from the left side. So the graph of the function is going to have to be sloping down with a slope near negative 1 for x less than 0 and up with a slope near 1 for x greater than 0, and so it'll end up having a cusp or corner there.
My gosh.
Also, notice that even if I weren't 100% sure that the derivative didn't exist at x equals 0, it's not going to hurt to consider this x equals 0 as a possible additional candidate for the absolute max or min value. So I've got my three critical numbers, and my endpoints are just going to be x equals negative 2 and x equals 2. So let me make a chart of values. My x values to consider are negative 2, negative 1/2, 0, 1/2, and positive 2. And my corresponding f of x values are going to be, let's see, absolute value of negative 2 minus negative 2 squared works out to 2 minus 4, which is negative 2. I plug in negative 1/2. I get 1/2 minus 1/4, which is 1/4. Plug in 0, I get 0. And plugging in 1/2, I get 1/4. And plugging in 2, I get negative 2 again. So now my biggest value is going to be 1/4. So that's my absolute max value. And my smallest value is going to be negative 2. So that's my absolute min value.
Guys, I think I've cracked it.
So here I've graphed my function y equals absolute value of x minus x squared on the interval from negative 2 to 2. And I can see indeed that my absolute min is going to be a value of negative 2. It occurs at 2 absolute minimum points. And my absolute maximum is going to be a value of about 1/4. And that occurs at 2 absolute maximum points. And that concludes this video on finding extreme values. The mean value theorem relates the average rate of change of a function on an interval to its instantaneous rate of change, or derivative. Let's assume that f is a function defined on a closed interval a, b, and maybe defined in some other places too. let's assume that f is continuous on the whole closed interval, and that it's differentiable on the interior of the interval. Then the mean value theorem says that there must be some number c in the interval ab such that the average rate of change of f on ab is equal to the derivative of f at c. In symbols, we can write the average rate of change as f of b minus f of a over b minus a, and that has to equal f prime at c for some number c. On the graph, the average rate of change of f is the slope of the secant line. And so the mean value theorem says that there's some number c somewhere in between a and b, so that the slope of the secant line is exactly the same as the slope of the tangent line at that x value of c. The number c is not necessarily unique, so I encourage you to pause the video and see if you can draw a graph of a function where there's more than one c value that works. So you might have drawn something maybe like this. Now if we draw our secant line, there's two values of c where the slope of the tangent line is equal to the slope of the secant line. In this example, we're asked to verify the mean value theorem for a particular function on a particular interval. Verify means that we need to check the hypotheses of the theorem hold, and also that the conclusion holds. The hypotheses are that f is continuous on the closed interval 1, 3, and that is differentiable on that interior of that interval. Both of these facts are true because f is a polynomial. Now we need to verify that the conclusion of the mean value theorem holds. In other words, we need to find a number c in the interval 1, 3 such that the derivative of f at c is equal to the average rate of change of f on the interval from 1 to 3. Now f prime of x is 6x squared minus 8, so f prime at any number c is just 6c squared minus 8. We can also compute f of 3 just by plugging in and get 31, and f of 1 is negative 5. Plugging in these values into our equation, we get that 6c squared minus 8 has to equal 31 minus negative 5 over 2. In other words, 6c squared minus 8 had better equal 18, which means that 6c squared needs to equal 24, so c squared has to equal 4, which means that c has to equal plus or minus 2. Since negative 2 is not in the interval from 1 to 3, we're left with a c value of positive 2. So c equals 2 is the number we're looking for, and at c equals 2, f prime is equal to 18, which is the average rate of change of f on the interval. We've verified the mean value theorem. In this example, we're told that f of 1 is 7, and that the derivative of f is bounded between negative 3 and negative 2 on the interval 1, 6. We're asked to find the biggest and smallest values that f of 6 could possibly be. Well, the mean value theorem gives us one way of relating the derivative of the function to its values on the endpoints of the interval. More specifically, the mean value theorem tells us that the average rate of change, f of 6 minus f of 1 over 6 minus 1, is equal to
that.
f prime of c for some c
Whoa.
in the interval 1, 6. Since the derivative is bounded between negative 3 and negative 2, we know that the average rate of change is bounded between negative 3 and negative 2. We know that f of 1 is 7, and now we can solve this inequality for f of 6. I'll multiply the inequality by 5 and add 7.
Yeah,
Now
I
we
think
can see
I've
that
got
negative
it.
8 is the smallest possible value for f of 6, and negative 3 is the largest possible. Rolle's theorem is an important special case of the mean value theorem. If f is a function defined on the closed interval ab, and f of x is continuous on that whole closed interval, differentiable on the interior of the interval, and if f of a is equal to f of b, then there's a number c in the interval ab such that f prime of c is 0. If we look at a graph of such a function that has equal values at a and at b, we can see where its derivative has to be 0, at a maximum or a minimum in between a and b. To see why the Rolle's theorem is a special case of the mean value theorem, think about what the mean value theorem would say about this function. It would
Yeah, I think we could just like skip forward to here.
In this video, we'll solve problems where we're given an equation for the derivative of the function, and we're given an initial condition, something like f of 1 equals 7, and we have to find the function f of x. In this first example, suppose g prime of x is e to the x minus 3 times sine x, and g of 2 pi is 5. We need to find g of x. Well, g of x is an antiderivative of e to the x minus 3 sine x, so g of x is of the form e to the x plus 3 cosine of x, plus a constant c. That's because the derivative of e to the x is e to the x, the derivative of cosine x is minus sine x, and the derivative of a constant is just 0. Now I need to find the value of the constant c that makes this initial condition come true. If I plug in 2 pi for x, I get e to the 2 pi plus 3 times cosine of 2 pi plus c, and that needs to equal 5. Since cosine of 2 pi is 1, I have that e to the 2 pi plus 3 plus c equals 5, and so c is equal to 2 minus e to the 2 pi. So my function g of x is equal to e to the x plus 3 cosine x plus 2 minus e to the 2 pi. In this example, we're given the second derivative of f, and we're given two initial conditions. F of 1 is 0, and f of 0 is 2. To start,
Oh my gosh, my pen.
x in a more manageable form. By distributing, I get the square root of x times x minus the square root of x.
Pen read out.
And rewriting with exponents,
And it
we get
was-
x to the 3 halves minus x to the minus 1 half.
Wow.
Next, I'm going to find f prime of x, which is the
Zero.
antiderivative of f double prime of x. So f prime of x, using the power rule for antiderivatives, I raise the exponent of 3 halves by 1 to get 5 halves, and then divide by the new exponent, 5 halves. Similarly, I raise negative 1 half by 1 to get 1 half, and divide by the new exponent, 1 half. And I'll add on a constant c. Let me simplify a little here. Instead of dividing by 5 halves, I'll multiply by 2 fifths. And instead of dividing by 1 half, I'll multiply by 2.
Chat, look.
Now I've got an expression for f prime of x, but I need an expression for f of x, which is the antiderivative of f prime. And so I'll
Here's my other teachings,
so now
you know.
2 fifths times x to the 7 halves.
Guys don't
plus 7 halves
understand.
Minus 2 times
I think
x to
I've
the 3
cracked
halves
it.
over 3 halves The antiderivative of
I think
a
I,
function c is
I think
c
I
times x,
finally
and then I
cracked
want
it,
the
you
constant
know.
d.
We
I
like
simplify
go
as
way
follows.
back. Like,
I'm going
look,
to use my initial conditions
you
to
know.
solve for my constants c and d. When I plug in 0 for x, all my x terms vanish, and I'm just left with d. So d has to equal 2.
I think I've got it.
So I can rewrite my function, setting d equal to 2. And now my second
Chat, I
function
literally
sets x
said
equals
4
0.
hours,
So
but I think
we
I've
get 4
cracked it.
35ths minus 4 thirds
Let me
plus
just,
c
let me just
plus 2.
calculate
And
my
that has to equal
final
0, which means that
teachings.
c is negative 2 minus 4 35ths plus 4 thirds, which simplifies to minus 82 105ths. If we plug that in for c, we get a final answer for f of x. And that finishes the problem. In this final example, we're not given any equations, so we have to make them up ourselves. We're told that we're standing at the edge of a cliff at height 30 meters. We throw a tomato up in the air at an initial velocity of 20 meters per second. The tomato then falls down to the ground due to gravity, and we want to find how long that takes and what its velocity is at impact. We know that the acceleration due to gravity is negative 9.8 meters per second squared if we're working in metric units. The similar figure, if we're working in units of feet, is
I've
negative
done
37
it.
feet per second squared.
I've literally done it, chat.
Gravity is pulling objects down towards
Oh
the ground
my
in the
gosh,
negative
they're
direction.
all my
We're also given the
teachings.
initial condition that velocity at time 0 is 20 meters per second. That's a positive velocity because
We're gonna ask.
and we're told that the initial
Chat, let's see. To pause this stream, I need to figure out this. Okay, this is 10 stuff. Just like move all this out of the way. This is the 10 stuff, chat. This is 10 stuff. Right. Right. Chat, enough with the games. Let's figure this out. Let's figure this out, chat. Alright. Frick. A pen. Limes. This. Okay. X3. We could just cross that out. X is to infinite times neg limes. Which leaves. Cross that out. Neg 200 equal infinite and a half. Go 1/2 minus half. Half. Minus 1 is with 5. 5 with 5. Positive, negative, positive, negative, positive, negative, positive, negative. Positive, neutral, negative, neutral, positive, neutral, negative. 5 cubed, which leaves infinite capacity, power 2. So it's not 0, it does not exist. It's either 2 or 4. That will be reinforces. 2 goes to 2. It's 2. It is literally 2. I was telling you guys it was 4. It's because I didn't carry that repeated 1. Holy cow. Now we gotta go to the next one. Know it straight away. Because this is easy, bro. Dude. I literally taught myself freaking calculus in 2 hours with Google. Three to 4 months. I did it in 2 hours. Holy cow, bro. I mastered it. All my teachings. Gone. Because if this power gets out, if my new teachings get out, all hell could rain loose. That's it for today. Shout out to my boy Sigma. Chat, we literally, in 2 hours, 2 freaking hours, I learned calculus. That's insane. Because GJ knows. You know? Freaking GJ knows everything. Dude, I taught myself how to learn calculus. Right. I'm too smart for this. Transcendent intelligence. Top chocolate.